we need to start this. Let me try. Of swarming is based on behavior of birds, and the work started by Craig Reynolds. I'm just showing you a Wikipedia page where the fundamentals of flocking has been defined actually very early, like 1980s. So the key things here are something called maintain some separation. These are the general principles of flocking, and alignment and cohesion. So two things, these three principles are necessary. One is separation. It doesn't matter whether they are birds or vehicles. There need to be minimum separation between between a pair of vehicles. Same thing with birds too. If you obviously we get so enchanted. It's so interesting to see flocks of birds, and there will be sometimes in tens, and sometimes in hundreds, and sometimes in thousands, but still even more actually. The numbers in some places will be very, very large, like tens of thousands of birds, but still they maintain so beautiful pattern, and you don't see birds falling down because of collision or any sort of accidents. So, so the fundamental rule is there should be some sort of a separation maintenance, and of course they're all aligned. It's also fascinating to observe that the movements are so elegant and also so quick, so fast. The direction, suppose say the whole flock is changing the direction. Is same thing with birds and also schools of fish. Now we see in National Geography videos such a beautiful patterns and moving so swiftly and smoothly without any accidents, without hitting each other, right? So those are the guidelines we follow for swarm, even intelligent swarms as well. So fundamentals are actually based on the inspiration actually comes from flocks of birds and school of fish. Again, you can, of course, you can review this later, but I just wanted to start from the beginning, okay? And then I will show you a punchline first. So to appreciate the research, we need to see something that actually catches your attention. So I'll show you the last slide first, and then we'll get into the details, okay? Give me a second. So this picture shows if the graph or the that is drawn based on the topology of the UAV swarm or swarm of aircraft, then look at the difference between the two pictures. Here, this is a regular graph. Regular graph means each node has the same degree. Now, what is the degree? How many nodes are connected to one node? Here, for example, the degree is 2. Whereas here the degree is not uniform. The degree is, some of them have degree 1 and some of them have degree 2. So where are these graphs coming from? They are coming from the topology of the network. And the network depicts the connectivity among the aircraft, for example, UAVs. So we're talking about UAV swarms, so we can assume that each node represents a UAV. And then we are we are representing the topology of the swarm in the form of a graph, and then we are looking at, if you represent in the form of a graph and study its behavior, and what is our performance metric, how we'll go into details, but I just wanted to quickly give you a punchline here. The performance is how many steps or how many iterations how many iterations it takes to converge. So we have to learn a lot of things here. One is, what do you mean by iteration? What do you mean by formation? We'll all get into that. So generally, the problem is called consensus building. Consensus means you agree on something. Okay. Now I'll give you a bunch of examples later. But so the point is, if you are able to pose the problem as a graph, and then the graph properties, in this case, if the graph is like this, it takes 60 iterations, and if the graph is like this, it takes 100 iterations. So what we want to do is, so what does it depend on? What are the factors that the convergence depend on? So that's what we are trying to we need to analyze. So first of all, iteration means, what does it mean, iteration? Basically, every node is sharing its information. Okay, and so how many times it has to share, and who do you think who is receiving the information? Each node is basically sharing its information, like on a regular basis. Let's say every step, we count in terms of steps rather than absolute time. So ultimately, we want to see how much time it takes to converge, but instead of answering in terms of absolute time, we look at how many steps it takes. Okay, the amount of time for each step depend on the computational power. So we don't have to get into that, but if you answer the question in terms of how many steps it takes. So what does each step contain? Each step includes sharing information with neighbors. All you are doing is, each node is sharing its information with others, and also at the same time it's also receiving the information. So basically, because the network is connected, each node at each step will share its own information and also receives information from its neighbors. So that's called one iteration. So in each iteration, you are sharing your information with others, and you are also receiving information from your neighbors. And at the end of the day, you are trying to solve a problem. What kind of problem? For example, a simple example is finding an average. So for example, since many people are working on wireless sensor networks, this is a good example of a static wireless network where each sensor is observing something, and it shares with its neighbors. And our goal is to see, in a simplest example, in a simplest scenario, we're trying to find the average value of whatever you are observing. For example, each node is measuring the temperature. Our goal is to see at every node should converge to the same average. For example, let's say each of the sensors here, each node represents a sensor, and each sensor is measuring the temperature. Then initial values may be different at each location. Even in this room, if you put a bunch of sensors, the temperature that you observe here may be different from the temperature you observe at some other in the corner. Okay, so the simplest problem of consensus building is to get an average, and the point is we have to converge to the same average, same value. Like that depends on the connect. You'll see how the connectivity plays a role. So for example, if number one is measuring, let's say 30 degrees Celsius, and this is measuring 31, maybe 32, 33, 34. Let's make it 31, 32, 33, 34, 35. Let's say each sensor is measuring such values. Then in each iteration, let's consider the first iteration. The first sensor is saying, okay, I measured a value of 31. It is sending to its two neighbors. And then same thing, every node follows the same process. Okay, so which means that if you focus on sensor 1, its own value is 31, and it is getting 32 from here and 35 from here. And what will it do? It will combine everything and divide by 3 in the first step. So that will be some number, and every node does the same. So that entire round consists constitutes one iteration. The question is, how many iterations does it take for all the nodes to converge to the same value? And it's a very interesting problem, but it is very well studied, and there are a lot of variations. I'm going to bring up what kind of new things we can do. But the main point is, we looked at a simple example of consensus building. And obviously the question comes, how many steps it takes? And the answer actually lies, surprisingly, in something called Laplacian matrix. So what is a Laplacian matrix? It's a function of two parameters. One is, for any graph, for example, take this graph or this graph, you can create an adjacency matrix. Most all of us know, if you looked into a matrix corresponding to a graph, the first thing that comes to mind is adjacency matrix, right? And which node is connected to what? For example, in this case, there are 5 nodes. You have a 5 by 5 matrix, and if you look at A12, first row, second column, it shows whether node 1 is connected to node 2 or not. That is required for Laplacian matrix is the degree of each node. So typically in the diagonal of the Laplacian matrix consists of degrees. So 1 element in the matrix is 2. So obviously since it's a regular graph, you'll see the diagonal elements are all 2s. But in this case, it's different. Okay. And then there is also, before you get into all the theoretical things, and then you also need to normalize the Laplacian matrix. So if you don't normalize, you will the results are you can explain in terms of Laplacian matrix or normalized Laplacian matrix. However, the results will be different if you don't normalize. Okay, so it's better to normalize the matrix and then derive your results. So the key thing is, it is interesting to see the eigenvalues capture the behavior or the characteristics of the graph, and especially the convergence. And one more feature or characteristic that is important is something called stability of the network. So stability, of course, it depends on again the degrees, because stability is something like, if you have taken a class in signals and systems, we define stability as of a system in general as something like, if the input is bounded, can the output also be bounded? So bounded input, bounded output. So for bounded input, can we assure output also is bounded? That is the definition of stability. But there are little more in control systems perspective. There are more rigorous definitions in terms of stability. But it is sufficient to understand that the idea of stability before you get into some more advanced metrics. The key point is, if you have a network of let's say vehicles or nodes, wireless sensor network, like a wireless sensor network, then if you can represent the topology in terms of a graph, and then by studying the behavior of the graph, characteristics of the graph, we can predict how many steps it takes or how many iterations does it take to converge. So convergence itself, or consensus building is a process, and convergence, it refers to when there's when do you stop, how many iterations are required, and at the end of the certain number of iterations, all the values will be the same, or you converge into certain whatever you are looking for. For example, if you are finding an average value, it is the simplest example. The other things are convergence of like a formation control. In fact, that is the problem we are going to discuss in detail later. So what do you mean by what is formation control? Let me give an example. Let's say you have a collection of UAVs, a bunch of UAVs. They're starting from different locations, and then they are going towards a common destination to accomplish some task, some mission. They're starting from different locations. For example, one could be starting from that corner, one could be from this corner, from maybe, and other vehicles from any random places. And then you define a pattern. You want to define a pattern. You want to form like a triangle or a some structure. You predefine the structure, and then each vehicle starts from different locations, and while going towards the destination, somewhere in the middle, you are expecting the formation to be complete. Now, suppose say you create a triangle pattern. Now, you have seen military jets and all that. They try to form a pattern when they are flying. So whatever pattern you decide, you define that structure, and then all these vehicles are going to go to their respective or expected positions. So consensus building in that scenario is how many iterations does it take, how many steps it takes for all the vehicles to come to the pattern. Okay, so ultimately they need to form the pattern before they go to the destination to accomplish a task. I'm going to show a little more details. Okay, give me a minute. So I also want to show you some interesting what I call properties of graphs that they're simple properties, but they're very interesting properties that will help us to what I call connect the graphs and graph properties to the problem that we are looking at, consensus building problem. So in terms of problems that you can solve on graphs, there are many. Lately, problem solving on graphs, also graphical neural networks, all these are becoming coming to the limelight. And there is also a lab called Bayesian lab. It's like a nice tool where you are using graphs as a foundation or a framework for solving problems, research problems. For example, there are a few other things. I talked about what I call the average, finding an average. That's the simplest problem. The other things are, you're trying to collect the data. The sensors are collecting the data. Right. Yeah. So that's also like you're computing on the network, in the network, like a graph. Basically, in terms of theory, you're defining a graph and you're solving problems on the graph. Then, right. The other things are like some estimation problems, tracking problem. So estimation is like estimation means for example, you're trying to fit the data to a known distribution, are you trying to find, like for example, if the distribution is a Gaussian distribution, your goal is to find what is the mean and standard deviation. So these are the kind of problems. There are even more advanced problems too, but basically there are a lot of things can be done, especially related to wireless sensor network, detection, prediction, estimation. These are the problems that you can solve. Okay. So what the example that we took is very simple. Let me take a minute. Say again. Right. It's a data fusion. Data fusion in the sense you're collecting the data and think about what are we doing with the data. Are you trying to fit it to a distribution? Are you trying to estimate something? Are you predict something? So those are the problems. Obviously, they depend on the network topology, and then that's the reason we need to use graphs as a graph properties or graph characteristic. Okay. So we'll get into the slide deck in a few minutes, but then I also want to show you one more work. So just like yesterday, this work also is in progress. I will discuss few interesting properties of graphs. One interesting aspect of graphs and mobile networks, mobile sensor networks is the idea of mobility. It's very fascinating to see, very interesting to see what is the impact of mobility. We talked about static graphs. We just saw a static graph, and you can solve the problem of how many iterations does it take. And as I told you, it depends on the convergence rate or convergence time depends on the on the eigenvalues, basically, especially the second eigenvalue. So I will leave it. I won't give more details, but look at on your own. Do your own homework to see why that second value is important. What about the first? Interestingly, the first, depending on how you define the Laplacian matrix, the first eigenvalue is always 0. In fact, the smallest eigenvalue is 0. You have to be careful though. It depends on how you define the matrix. Okay, but if you normalize, then look at the eigenvalues of that of the matrix. So basically, you take the topology and create a graph, and then from the graph you define adjacency matrix. From degree and distribution, you can create a Laplacian matrix. And then you are talking about eigenvalues. So what is the nature of these eigenvalues? The first eigenvalue is the smallest. Basically, they are ordered smallest to largest, and that eigenvalue is 0. Okay. Then the second eigenvalue will actually tell you. You point normally, depending on how you define the matrix, it will be 1, but in this case it is 0. Okay. But what you're thinking is, yeah, does it mean the graph is isolated? No, it's not that case. Yeah, it is not disconnected. It's assuming it is connected, but if you order the eigenvalues for this type of matrix, the eigenvalue is good. I'll show you. I'll give you some more details. So here are the properties of for static graph. Now I asked my student, let's understand what we know, and then with our objective is to study the impact of mobility on the convergence rate. How fast does it converge? Say again. Well, no. Convergence, basically, how many steps does it take? No, not degree of 2. For example, for any consensus problem. So, for example, we talked about finding an average, right, earlier. Yeah, we talked about finding the average, right? Is it okay? Yeah, can you hear me now? Can you hear me now? Okay. So look at the problem is, in a simple example is you're trying to find average, and because you cannot find average at the one shot because you don't have all the values. It's more like not all nodes are connected. It's not a fully connected network. If it's fully connected network, it's only one step. Right. Yeah. So right. Basically, each node computes the average based on the information it has. So the question is, how many rounds we have to share information, or how many iterations does it take to make sure that every node has the same value? Yeah. So the answer to that, interestingly, lies on the second eigenvalue of the Laplacian matrix. Okay. So that led to really understanding the eigenvalue properties. So right, yeah. Right. Yes, I will actually give me 1 second. Is in a process. My goal is to just show you what are the properties of the static network. And when you go into mobile network, then the impact of mobility becomes critical, and that depends on there are research studies done on mobile network also. I'll give you some known results or known concepts, and then there is a lot more research to be done. So the first thing is, make sure that you're actually looking at the normalized Laplacian matrix. That's number one. So in fact, how does the normalized matrix look like? The nature is it's a row stochastic matrix. So that is the nature. Okay. So I won't go into too many details, but look at these properties. The eigenvalues lie between 0 and 2. These are the basic definition that we know. You can read some papers on your own and come to understand these things. But these are the known results. First smallest eigenvalue is 0, and then second smallest eigenvalue is less than or equal to n over n minus 1, and the largest eigenvalue is greater than n over n minus 1, and sum of all eigenvalues equal to n. Say again. Manhattan network. Well, yeah, I didn't. Basically, whatever be the network, you can design the Laplacian matrix corresponding to that. I'm only looking at the Laplacian matrix. Okay, and then see the largest. There are some. These are the known facts. The product of all eigenvalues is n by n minus 1 power n minus 1. Actually, yeah. So these are some of the known values. Yeah. The point is, for mobile ad hoc network, what are the things that you can what are the nature? What is the nature? What is the behavior? Because that is if it is a network is static, then we are good. We know all this. But what if the network is mobile? Okay, like why are we getting into mobile ad hoc network? We're talking about swarms. We want to understand the swarm behavior. Once again, look at the concept of consensus. Consensus building means you're trying to agree on something. It could be just a number. It could be like an average value, or it could be something like formation control. For all this, or it could be some sort of an estimation problem. All this could be mapped onto into something called consensus building. And then the question is, the fundamental question is, how many iterations does it take? That's what we're trying to answer. Once again, you can see that this problem is definitely an interdisciplinary problem. And if you work with a mathematics professor who has already done a lot of work on graph theory, it becomes much easier for you to for example, if you are getting some results and then you want to see whether the results are meaningful or not, definitely the experienced professor in graph theory, they may be able to help you. The second thing is, so the second thing is that maybe it's a couple of points I want to make. One is, whenever you're doing research in subjects like wireless sensor networks, it's not about practical aspects only, but it will be interesting to derive some theoretical results. Because without theory, no matter how much research you do and show results, you cannot really it would be insufficient in the sense, and you cannot prove that that's the best you did without theoretical. Like for example, if you are looking at any performance, what is the best performance? You don't know what's the best performance unless just because you're doing a lot of experiments. So there should be some sort of bounds in terms of what. Okay, like for example, when we look at compression or channel capacity, then in terms of compression, there are some bounds in terms of how much you can compress. The same way, in terms of data rate, capacity is the maximum achievable data rate. So without that, no matter how many experiments you do, you cannot say your results are best or better. So in that context, especially when you are working on wireless sensor networks or mobile ad hoc networks, it is important to connect to graph theory, so that graph theory will actually tell you what's the best you can achieve. So for example, that's the reason here we're saying that your behavior of convergence, especially how many steps does it take, it is dictated by the graph theory. Okay? So that's where Laplacian matrix comes into picture. Yeah. Okay, maybe I'm sure actually you can find what is the Laplacian matrix and how to construct it and all these properties that I was talking about. You can also look on the literature. It takes some time. uh, So what we are trying to do is first enumerate everything that you know, and then next step is we're looking at what are the new results we can get, especially when you consider bring mobility into the picture. Anyway, so that is the idea here. Now let's go back to our main topic. This work was done by Srijata Mukherjee. She was my PhD student. She graduated in 2021, I believe. Now she's working for GE, General Electric. So in this presentation, we will review flocking and collision avoidance. Two things. We want the vehicles to be closer so that they can talk to each other. They are within the communication range. At the same time, you want to make sure that they don't hit each other, they don't collide. So there are two aspects. One is be together, close enough to be able to share information, but not too close for avoiding any collision. So that's the problem. And we are depending on graph theory. As I said, the answers are in the graph theory. And the problem is called consensus problem, consensus building. Even though I just gave a smallest example of finding an average to begin with, but even the formation control itself is a consensus building problem. So, I mean, so there are obviously the problems are different. In one case, you're trying to estimate some value like a parameter, value of a parameter like mean and maybe standard deviation, those kind of things. But in the other problem is here we're talking about how many steps does it take for all these nodes, all these vehicles to form the pattern. Both are related. In one case you're dealing with the data. In the second case you're expecting each vehicle to go to the expected relative position. So formation control is actually defined as a in terms of relative positions. For example, if you say all the vehicles have to form into a triangle, if the three vehicles are there, then there are three vertices. But if there are five, then maybe you can again create a triangular pattern. For example, I'll take a small group. So there are three nodes. You're talking about three vehicles to begin, or maybe there are more. Now you can have five vehicles too, or maybe six. So when I say pattern, this is an example of such. So we want, irrespective of where they started, you want the vehicle during the while they are flying, they may be starting at a different position. Let's say this is our starting position. S1, S2, S3, S4, S5. So they are starting randomly, but you want them to converge to this pattern before they go to the destination. I'll show you a little more details later. That is what is meant by formation control. The degree distribution concept here is that based on the degree distribution, you can answer this question, how much time it takes to form. So degree distribution plays a role. For example, in the previous graphs I showed you, we were referring to like in one graph, it's a regular graph. The other graph is an irregular graph or skewed graph. So you can estimate, or you can ask, of course, degree distribution will dictate eigenvalue distribution. So based on the eigenvalues, you can answer this question. You can answer this question of how much time it takes to converge. So the input is degree distribution, and the output is eigenvalue structure, and eigenvalue structure will answer the question we want to answer. Like for example, so basically the topology of the network is defined by degree distribution, and degree distribution, based on the degree distribution, you can estimate the eigenstructure, and the eigenstructure is going to answer our question. Anyway, so that's the general idea. So we get into some finer details, the mathematics. Let's go take time to understand as much as we can. So to begin with, swarm, the definition of swarm. In the literature, you can see like a multiple agent system, MAS. They call, if you look at the literature, you will see those kind of terms, multi-agent system or MAS. And it could be ground vehicles, it could be UAVs. UV stands for underwater. These are the general real world situations, and they're all working towards a specific mission. So that's the definition of swarm. Swarm behavior includes flocking and deconfliction. But these are sort of opposing directions. On one hand, you want them to be closer, but you want them to make sure that there are no conflicts. Conflict means they don't hit each other. And behavior, in terms of behavior and problems related to control systems, formation control is a control systems problem. And the objective is, in the case of intelligent swarms, which is our topic, to achieve a desired formation pattern as quickly as possible. Okay, again, and as I drew on the board, the vehicles are randomly located, but they're all coming to expected positions in the shortest time possible. That's our goal. You will have lots of questions if you think through. Okay, but you, of course, feel free to ask me. But we are, even though I'm actually guiding you towards a particular problem, there will be lots of questions in your mind, and we will try to answer as much as possible. So first thing is, map onto a graph. I'll take time to go through this so that when you see all these variables in the next few slides, you should be able to connect and understand what exactly is being done. So first thing is graph. Typically, graph consists of vertices and edges. That's kind of simple. And the adjacency matrix definition is that there are two things: adjacency matrix and Laplacian matrix. Adjacency matrix is, if you have n number of nodes, then the matrix will be n times n dimension, and the element aij, referring to ith column and ith row and jth column, will be 1 if there is a connection between I and j. If I and j are connected, element aij will be 1. That means there is an edge. The meaning of edge is kind of interesting. You can assume that those nodes are within the radio range. They're able to communicate. And some later actually we'll come across into a situation where, is it a physical connection or a logical connection? Basically, physical means they are physically close. Logical means they're communicating. But for communication, you don't have to be physically close. For example, like I talk to my family members, they're not here. I'm talking to you, but you are here. So ours is a physical neighborhood. We are physically close. But even though my friends are far, they're not my neighbors now. Physically, not my neighbors, but I'm able to communicate. So basically, you're going to, when we are solving the problem, we have to come up with, is it a physical neighbor or logical neighbor? And interestingly, you will see why that is important later. Okay. So it is possible that you have a physical neighbor, but you don't have to talk. You don't have to communicate. But at the same time, if the two vehicles are physically close, you have to avoid collision. So with respect to a logical neighbor, you don't have to worry about collision, but you are sharing information. So that concept will arise a bit later. Okay, let's look into what's the meaning of Laplacian matrix. Follow this carefully. Yeah. Adjacency matrix is clear, right? Degree matrix is only diagonal, the diagonal matrix. And yeah, if I equal to j, the degree is the value is 1, otherwise 0. In fact, it's possible that there may be, each node may be connected to many neighbors. In that case, you are actually putting the value of the degree. So it's not 1 in that case. So degree in fact, maybe let's make the correction. What I'm saying is, if the degree can be more than 1, right? So in that case, if you okay, right, you're right. So because you're only talking about ij, for example, if node 1 is connected to node 2, node 3, node 4, then you in the first row you're going to see many more, right? Laplacian matrix is follow this. Degree ij if I equal to j. And minus 1 if I is not equal to j, and vi is adjacent to it. In fact, it's better to look around on the Google and see what's the Laplacian. But let's take some time, because it's very critical for us to make sure that we understand this term a little more clearly.
It's similar to 4 adjacency or 8 adjacency.
No, yeah, one minute. Actually, I wanted to show. Yeah, this is what I wanted to show. In fact, Laplacian matrix is D minus A. D is the degree matrix, A is adjacent. That's as simple as that. Okay? So diagonal matrix is it only has diagonal entries. Yeah, then look at it. Dij equal to, yeah, this is let's follow this structure. Dij is Di. The degree of the node I is coming in the diagonal. So it's more than 1. It could be more than 1. And then Laplacian matrix is D minus A. What about normalized Laplacian? Let's look at that too. If you, this is a little bit more complicated if you look at this notation. Give me one more minute, and then these definitions are little important before we go further. So we talked about Laplacian. Yeah, it's I minus A. Yeah, normalized Laplacian is I minus A. I is the identity matrix. So this is I think it's the simplest way to look at. So we define Laplacian as D minus A, and then the normalized Laplacian is I minus A. So further normalized Laplacian, if you look at the eigenvalues, then all the things that I talked about before, the properties hold good. Okay. Now let's talk about consensus building. It's basically a control technique applied to relevant to multi-agent systems, and the idea here is to reach an agreement or agree on something or reach a desired state. Maybe that's even better. State means like in the case of formation, the desired state is to be in a specific relative position. Now, for example, here, no matter where we started, the node 1 is supposed to be at this location, and other nodes are their positions are given here. And the key thing here is the relative positions. And it's like, for example, let's call one of them as a leader, and depending on where this node is located, this node has to maintain the relative position accordingly. Same thing with others too. So obviously you cannot fix the location. The position of the node 2 depends on position of the node 1, because we're talking about all these are like flying together. So if one position of one node changes, all other nodes have to follow. So if it is a static graph, everything is fixed, but the node positions are fixed. But if it is moving with a dynamic graph, then the node positions are defined in terms of relatively defined.
Like a Markov.
Yeah, it's more like a geometry for now. What is the position of node 1? Or if let's fix one of them. Let's say S1 is fixed. Then what is the position of S2? What is the position of S3? Those are relatively defined. So we are going to see those things in a minute. Okay. So in terms of formation control related to UAVs, it's a cooperative control strategy for a group of UAVs to reach a predefined configuration. And here is an example of what we talk. It's a predefined configuration while maintaining the pattern. So in fact, both are kind of same. Whether it is a pattern or a predefined configuration, both are kind of same. And of course, we need to look at the connectivity among the agents. So what this means is, if you draw a graph like this, it means that that you are showing. If the graph is exactly like this, then you are showing that 2 and 3 are connected, 1 and 2 are connected, but 2 and 6 are not connected. But of course, I just drew a triangle. It could be different form. You can have a different pattern. So the pattern, the point is the pattern of connectivity that will tell you that will define the Laplacian matrix, and from there your what you call how fast you can converge, how fast you come into this pattern is dictated by that connectivity. So what do you mean by connectivity? When two nodes are connected, you are able to share information. Okay? So basically, the communication pattern depends on the connectivity, and then based on the communication, information is being shared. So connectivity defines the communication, or in general, connectivity defines how information is being shared, and then the pattern of connectivity will define will define the matrix and the topology and the matrix will tell us how fast you are going to reach this formation. In fact, let me show you the results, final results. That way, you actually understand what we are trying to do. So here is a result. So here we are showing there are about five flights. 1, 2, 3, 4. There are basically 5 lines are there, right? So each of these curve rather trajectory is followed by one of the UAVs. So basically, this multiple or 5 UAVs are at different locations, and our goal is to reach this pattern. It's like something like a triangle pattern. So what is being shown here is, irrespective of where they started, how fast they can converge into a given pattern. So that is the problem. So there are 5 agents, and one of them is designated as a leader. because the designation of leader is important because one of them has to lead, and the others have to follow. So the question here is, the problem is called formation control, and then you are trying to find out how long does it take to come to this pattern, to form the pattern. Okay, that is the problem. And the goal is, why is this relevant? You are achieving certain mission, maybe whether it's a search and rescue operation in civilian world, or maybe a military mission. Like think of like these are like fighter jets. All of them are, they start from somewhere. Maybe each one is from a different ship, and then all of them are forming a pattern before actually accomplishing their task or completing their mission. So that's the general idea. Yeah. And feel free to ask me questions, but now let's get into the finer details.
In this scenario, convergence is settling of sensors into the respective positions.
Yeah, settling or reaching a formation. Like, say, remember, notice this. S1 is here, S2 is here, S3 is here. But ultimately, we want each of them to go to their respective positions. In fact, respective relative positions. Okay? Let's say, for example, this S3 is the leader. Then S2 has to follow S3 on the left side, and S4 has to follow the leader on the right side. Okay? And then S1 has to should be behind S2, and S5 has to be behind S4. But there is a clear-cut spatial pattern that we want to follow. So how many steps does it take to fall into this pattern? That is the problem. But what does it depend on? It depends on which node is connected to which. So that is the reason we are looking at the topology of the graph. And then ultimately, the eigenvalues will give us the answer. The question is our question of how many steps it takes. It depends on the eigenvalue structure.
So it depends on the second eigenvalue of the left.
Yeah, generally, if you see, normally when you look at the literature, many papers talk about this, and the answer is yes. Answer is actually second eigenvalue. So the question is, why second eigenvalue? And what about third? What about fourth? What about fifth? That is the normal question asked. Why second eigenvalue? So one answer is, we know that the smallest eigenvalue is 0 for the normalized Laplacian matrix. So that's by design. Okay, that's the nature actually. The closest eigenvalue is the next smallest eigenvalue. 0 is the smallest eigenvalue, which is 0. First eigenvalue, which is 0. And the second one actually tells you the stability. But what about third and fourth and fifth? It's worthwhile to study what is the nature of. But the answer is correct. Whatever you said, how many steps does it take, or how much time it takes to converge? It depends on the second eigenvalue. It also, in fact, second eigenvalue also tells you about the stability of the network too. So stability is, really speaking, is another interesting control systems related problem or parameter. Like normally, as I mentioned before, stability refers to if there is a small disturbance, then how quickly the system can come back to normalcy. That's a simple meaning of the spirit behind the stability. But there are lot more involved on this. For now, we are focusing on consensus building, but these are related. Stability is also related to sort of consensus building. So let's look at those definitions, these terms a little more. We have enough time, so we'll go through a little more in detail so that you can appreciate the problem formulation and the solution. So these are example graphs, and this is not a regular graph. Some nodes have degree 3, some nodes have degree 4, and some have only 2. Okay, P stands for position, V stands for velocity. So P dot, there is a dot here. So if you take the derivative of P, you get V, and then take the derivative of V, you get acceleration. So P for position, V for velocity, and U for acceleration. And I subscript stands for the age and time. and this is undirected graph. You are representing like an undirected graph. And then notice this. D stands for relative position. So think of dr as a set of all positions. That means, yeah, like for all the, it's a set of positions and a set of relative positions. And what do you mean by relative position? PID minus PJD. I and J. No, your D stands for, capital D stands for the desired position. So if you take two nodes I and J, and suppose this is our desired pattern. Let's take 1 and 2. So no, you can use this. You can substitute here. The position of 1 is P1D. The position of, let's say j equal to 2, I equal to 1 and j equal to 2. So P1D stands for position of node 1. P2D stands for position of 2. That's a desired pattern. You want remember it's a relative pattern, not a fixed location, not a fixed pattern. Because as you are flying, we want to have this kind of formation control or this kind of formation pattern. And no matter where they are, you want to have this kind of relative positions. So that's the reason. Obviously, position is a two-dimensional, right? There is a x and y. So if you look at you can separate them very clearly. Start with x position and y position. You have two parameters, right? So take x location of 1 and x location of 2 and subtract. That gives you the relative position, isn't it? If you subtract x1 and minus x2, it will give you the distance will be relative distance. And same thing will say you can do for x coordinate as well as y coordinate. So you can clearly separate x and y coordinates and come up with the relative positions corresponding to all these 5. Yeah. So just start thinking about substituting I equal to 1 and j equal to 2 in your mind, then you will be able to appreciate. Okay. We'll go further, and then again I'll try to focus on the concepts, and then once the slides, you have access to the slides, you can start looking at taking some examples. So what we define here is something called collision zone and interaction zone. Some of these ideas or concepts are derived by my student, but some of them are based on the literature as well. So, for example, this red circle is a collision zone. That means if thinking about one vehicle, suppose this is vehicle 1. So all these circles are related to one vehicle. Focus on one vehicle. So vehicle 1. So vehicle 1 is here, and you don't want any other vehicle to come within this dashed zone. If it crosses this and gets closer to this with a small circle, then there is an accident. So no matter what, no other vehicle should come within the small circle. So you need to stop it before. If you find another vehicle coming within this red circle, you need to stop. If it is within the red circle, you are in trouble. And if it crosses the small circle, then definitely there is an accident. So we don't even talk about, let's ignore the small circle, focus on the dashed circle. So that's R dash, okay? R dash is our boundary. So we want to make sure that no other vehicle comes within the dash circle. So that is called collision. So collision zone is defined as for each vehicle I. Time is also important because it's a mobile network, right? So time is also at a given time t for a node I. If the position of ij is between 0 and r dash, and for every j belong to the for every j, there is a j here, right? I and j. So every j belonging to the set of vertices. So for example, 1, 2, 3, 4, 5, 6. So V is all the nodes. For every J, collision zone is defined as CIT 0 if no node is present. But if suppose say J equal to 2 is present, then you are saying within the collision zone there is a node 2, and then you are looking at how are you including that. So to think about it, basically you are looking at which nodes are within the collision zone. This is what you are trying to observe. Which nodes are within the collision zone and which nodes are in the interaction zone. So if it is in collision zone, then we are in trouble. We need to get it out. Get rid of it. Push that out. If the vehicles are, we want the vehicles to be within the interaction zone, because that way you can communicate. If the node is within the big circle, it's good. But as long as they are not within the red circle, we are fine. If it is within the red circle, we have to push it away. And if the vehicle is not within the big circle, we want to bring them closer. So that is the idea. We want to bring the vehicles closer to us, but not too close to get into an accident. So what are we trying to do here? Which are the nodes within the collision zone? You're trying to estimate, trying to figure out, and which are the nodes. So all J's that are within the interaction zone, that is the big circle, are in the IJ, and all the nodes which are in the red circle are in CIJ. So basically, out of all the nodes, focusing with respect to just one node, let's say S1. For each I, you are trying to compute this. For each I, you are trying to compute which are the nodes within the collision zone and which are the nodes within the interaction. I hope that makes sense, right?
You see practical. If the vehicle battery decreases, communication rate also decreases.
Right, yeah.
That conditions are not issued.
Right, for now we are assuming that an ideal situation. Yeah. So in fact, really speaking, when you look into swarms, the issues like what if you are sending a message but message didn't receive? So those are uncertainty issues have to be studied more. They add actually some challenges. So fundamental idea of consensus building, formation control has been done long time back. But so, for example, if you write a paper on formation control only, most likely it will be rejected because it's nothing new. But if you add how to handle the latency issues, or how to handle uncertainties due to or some sort of a failures, then it will be more interesting. But if it is only just a formation control, that problem has already been solved. Just for the sake of students, you always have to come up with even while choosing the problem, make sure that your problem is something new. Otherwise, what happens is you work hard and then submit a paper, unless there is some novelty, or even it's incremental. You have to show clearly what is your contribution compared to the literature. Otherwise, for example, I see a lot of papers coming in routing algorithms, and there's not much. It's very difficult for any reviewer, or other reviewers will say, "Oh, I didn't find anything new," and they reject right away. But so you need to think about, if you take especially something like a routing algorithm or security algorithm, you have to really make sure that your work is something different, something new that you have added. But if you take a totally new problem, like problem that I was talking about before, like yesterday and day before, then you are right. You're the front runner, and there is not much work has been done. But if you pick up like problems like consensus building, many of these problems have been solved decades ago. So you will be at a disadvantage if you pick something that is well studied. But if you do, of course, you're who knows, you may be coming up with some new idea. But make sure that whatever work you are focusing on, you are doing something that has not been done before. So otherwise, If the review process takes about 3 to 6 months, you will be at a disadvantage. And after 6 months, your paper gets rejected, then you don't know what to do, especially you are trying to graduate soon. So it's very important to begin with, pick a problem that has not been done before. Or definitely you should have an idea about you are going to get some results that are different from what you find in the literature. So you have to put a lot of efforts in the beginning. Yeah. All right, I think we can do that.
Just for 5-10 minutes, you can have a break.
Yeah. My goal is to make sure we are, I want you to take away something from this lecture, so I'm going to do a little bit slowly. And then, of course, we'll share some publications later.
I said to tell you the book, you are now free problems.
Right, okay. Yeah. Since we don't have a restrictions in terms of it's a conference paper, you only have 15 minutes. And sometimes the work may be great, but we don't know how much we can get from it, right? So here the problem is I want to show how we define the problem and how we solve the problem. Now, by the way, this is a PhD student's work. Some of the work is based on the existing literature, but some terms and concepts we presented. For example, this kind of collision zone, and then the interaction zone. Some of these are defined by my student. The other thing that we introduced is logical neighbors and physical neighbors. So, all right, we'll take a few minutes break. The nodes that are already connected, as per your pattern. For example, node 1 has neighbors as node 2 and 6. So you want 2 and 6 to be always within the region, but not too close. So that leads to something called repulsive force and consensus force. Now we're saying consensus force means you want those nodes which are your neighbors to be within the large circle. Those nodes which are at the same time you don't want them to be beyond the red circle. Okay, so using some physical models, force models, we come up with two concepts, repulsive force and consensus force.
Is there any mathematics saying that collision zone, there's some math operator intersection zone or something like that? Because they have to come to the control input, there should be some threshold values.
Right, yeah. Yeah, let's look at the whole for a few more slides and then come back to this. So again, the student actually thought about these ideas. So there is
actually a good idea. Instead of draining the battery on one drone, they taking the help of all the drones and trying to push the globe node into the place.
Yeah. Also, the implementation is interestingly distributed. You are focusing on every node. At every node, you are modeling like this, and then your control input. Control input is a summation of both forces. Yeah. Now let's look into little more details. So the big picture here is you have a network. Then there is the feedback, and but typically you can see that the key parameter of this feedback is only the acceleration. UI stands for acceleration. Again, this is for every node. Okay. This model is applicable to every UAV. In fact, there are two categories. One is the leader, the control input for the leader, and control the same again control scheme for the followers. So these two are different for every. In this case, for example, if you assume that 3 is the leader, then there is one model for the leader, and for the rest of them there is a different model. So you're going to see that too. And keep in mind, P dot stands for velocity, and P stands for position, and D stands for desired information, desired position. Everything is about position anyway. No, where should the vehicle be? That's the question we are looking at. As they are flying, the positions is the one we need to make sure that each vehicle in the correct position. So all this is about placing each vehicle at the right location in the relative geometry. So the geometry has to be maintained. And even though the vehicles are in different places to begin with, all of them have to try to go to the desired location, right? Over the time. It's like, it's not going to be like in one instant. S1, for example, in this case, S1 is some location, but we want it to be relatively at this location with respect to the neighbors. So it's basically a distributed problem. It's a distributed system.
So the PI value they get it from GPS.
PI value is it is like it requires current location and desired location. You're trying to make sure that, of course, we need to know through GPS what is your location, and then what is your desired location relative to the other vehicles, and our goal is to go to that location and minimize the distance between your current location and the desired location. So while you are trying to be closer, be within the pattern or follow the pattern, you also have to avoid that you have to maintain the minimum distance. So I hope you can see the general idea of control scheme. Of course, you won't be able to understand everything, because there's a little bit of mathematics here, but as long as you get the big picture, it is fine. Okay. And now look at we talked about force. Remember, it is at every location for every node, and then this is about consensus force, and P stands for the position. So notice you are trying to you're looking at all your neighbors. For every j that belongs to the neighborhood of I, Ni stands for neighborhood. What is Ni? Ni is a set of neighbors basically. So who are your neighbors? Who are your neighbors here? Yeah, for example.
It's okay.
It's not working. Give me a second.
Yeah, recording.
We have been trying to ensure our two drones are in the communicating zone, but not in the collision zone.
Yeah, that's
correct, right?
So the consensus force is trying to put them to bring closer, and the repulsive force is pushing away from the collision. So that's the general.
How do we track the distance between these two nodes using a round trip time kind of calculation, or for instance, I am at this distance from my adjacent node?
It's been position so. So the GPS, you exchange your GPS value, I'll exchange my GPS value. You calculate those, I calculate. That's what P minus P.
P is the position.
PJ is the position of adjacent.
There are some assumptions here. You see, you are assuming that you know your location, of course, through GPS, and you also are assuming that your neighbor's location also is known. All these calculations are happening in every node, right? So in this case, focus on I. I is subscript I stays at I UAV. You are doing this calculation. That means every drone is doing this calculation. So it means that if you look at node I, Pi is its own location. Pj is
Neighbor.
location of its neighbor. So what is the assumption here? You are assuming that you know the neighbor's location. How do you know your neighbor's location? Because you are connected, you are receiving messages. Okay, so the idea here is every node is computing the same thing. And more specifically, if I is the node, this is the computation that node I is doing. And what is it doing? It is actually looking at all its neighbors. Ni is a set of neighbors, and you are doing the summation for all the j's. And I'll quickly describe, and then you can read the paper later. Kp is some sort of a gain. Okay. Kr is the velocity feedback. Kp is the position feedback, and P dot, don't ignore this dot here. P is the position, P dot is the velocity. And what this is telling you is, very quickly, it is trying to find the distance between I and j, and then difference between velocities of I and j. And then this is also an important point. What is dij? Let's go back to one step. It's important to know the values a little more. Pi is the ith position, or the position of the node I. Pj is the position of node j, and d is the desired location. And obviously, because if you consider two coordinates x, y, then there will be two values, two separate values. But if you think about 3D, there will be three different values for desired location or desired value of with respect to x coordinate, with respect to y coordinate, with respect to z coordinate. In some sense, you can handle them in three different ways. Focus on x and do something, focus on y, you can do something, because there are three dimensions, you would have to do three computations. But in simple sense, we are saying that dr is the desired pattern in general, and then with respect to two nodes I and j, you are looking at the desired portion of I, desired portion of j, and then subtracting. So notice, it is important for us to really appreciate this equation. So this addressing the relative desired positions, and these are the current positions and current velocities. So basically, the force, what you call consensus force, is a function of these parameters. And now look at this picture. Now what is happening? Here is an agent. It is giving out its current position, and then you are estimating this error from current location or current position minus desired position. Basically saying how much is the difference between current position versus desired position, and that is going as input. And then from the network, you are also receiving DRI. So what is DRI? With respect to, is it for the entire set? Now you are actually computing this for the graph or subgraph at least. And then this input is going to the controller, and what is the controller giving? What is the acceleration? Right. It's basically giving the acceleration for the node I. I think that's good enough for now. Again, I don't expect that we know everything, especially if you are looking at this first time. But just to give you an idea about how we are adjusting, how we are getting the feedback from the controller for each agent. This for the followers. I think for the leader, it's almost similar, but here is the equation for the leader. The force, consensus force for the leader. Probably there is another term here. The difference between this and the for the leader and follower is there is another term here, which is something called a tracking component. Yeah, I won't go too much into detail, but let's take a minute to appreciate what it is. See, one stands for the leader. So one of them you fix as a leader, and for the leader, this control input is slightly different compared to the forward. So we fix the node. We assume that node 1 is the leader. Again, the terms are the same. The variables are the same, but the equation for the leader is different because it can move on its own. It has some freedom compared to the followers. Followers have to, all the other nodes have to follow the leader, but leader has the freedom. So maybe that could be that's the difference. And there are some references we give. A lot of work has been done in this about 10 years ago. Okay. So far we talked about consensus force, meaning that you are trying to bring the nodes which you are with that your neighbors and keep them within the vicinity. For example, node 1 is trying to keep node 2 and node 6 together, close to it. And then everything is relative to the leader. So suppose the first one is the leader. While the leader is moving, we are trying to make sure that all other nodes are relatively in this pattern. Okay. Now the second part is the repulsive force. The idea here is to repel, to maintain the minimum distance, so that none of the nodes, again focusing on node I. If I is our focus, node I is our focus. We don't want all the nodes, any node actually come closer or within the collision zone. So let's see how that is done. So first of all, you need to come up with a function to maintain the separation, so repulsive force is modeled in this function. Dis stands for distance, A is some constant. So you're using some sort of a function for the repulsive force. Okay, it's not like there's nothing like a fixed set in stone, but it seems like this is an example, a good example for defining the repulsive force. So take a look at this. So we're saying that repulsive potential function, some function that describes the repulsive force. How is it defined? Again, it depends on the distance, Pj minus Pi. Then it depends on the number of nodes within the Ci. What is Ci? The collision zone. So you're looking at if any node enters within the collision zone, that forms a set. So you're looking at a set of nodes that are within the collision zone, and you're trying to come up with this function. So let's take a minute. Let's see whether we can interpret this succinctly. So this is the overall potential force, and that is a summation of this function, a repulsive function, that includes all the nodes within this red circle. So basically, the idea here is if there are any nodes that are within this circle C, you want them to push away. And you are defining some gain functions. Again, to get more details, there is a reference here. I think we can leave it there. Okay, I will move on to the next slide. So basically to putting them together, the control input, what is control input? It is giving out the acceleration for each node. Now U stands for the acceleration. It's a combination of repulsive force and consensus force. And for the follower, basically there are two different equations, one for the leader and one for all the followers. So we are assuming that node 1 is the leader. I think it is, we talked about these terms before, but make sure that that you know once you understand the meaning of each term, I think then you will be able to appreciate. Maybe something that you need to know is, let's take a few minutes again to spend some few minutes to appreciate the overall idea behind this. So Ni is the neighbors. So basically you are evaluating this for all the neighbors of node I. So once again, if you see, say node 3, the neighbors are only 2. You're not looking at everything, you're only looking at the neighbors. If you look at node 1, the neighbors are node 2 and node 6. So that is the idea here. Ni is a neighbor for all the neighboring nodes, a set of all the neighboring nodes. So for each j that is a neighbor of I, you are computing all this. Kp is some constant, Kp and K are constants, and sometimes you may have to play with those values to something like Tyler and there is no specific, although there are some guidelines, but Kp and K are constants, but they need to be defined based on some trials and experiments. And P is known. P dot is the velocity, and then this is the phi function that we just talked about for the repulsive force, and it is also very similar. Okay, once again, don't worry too much about if you don't get everything, but generally these are the equations corresponding to control inputs corresponding to leader and follower. So there is some discussion on the stability. We'll go over. We'll try to make sense of at least some of the ideas. Think of, we're looking at a set. Okay, for example, when you say PD, you're looking at desired positions, and P is the current position. So, but it's not just one node. We're looking at the entire set, entire graph, and coming up with the more like P represents the positions of all the variables, all the nodes, and PD is the desired position of all the nodes. So even though you're writing only one equation, but you need to split into like vectors. And U is the acceleration. Now this is the leader rule. It's called they use the terms like control law or control input corresponding to node I, and gamma is like a constant, and you talked about Kp, Kr, all that before. So it's all, now this seems to be a bit familiar, right? Now Ui and this sort of trying to simplify this, and then when you simplify, then there are things like x and x dot, which are briefly explained here. And if you look at if you oversimplify, then you come up with an equation. There are a lot of things here. See how you are simplifying. All of the same. Ui and Ui, both these are same, and you are kind of calling, you are denoting some big expression into x and x dot. So for example, take a look at gamma. And this is I think straightforward. This part is same as this, but look at this part. When you say KPLX, what exactly you are doing? You are combining the terms that have kp, like this is one part and this is another part, and whatever you factorize, that factor you are calling x, and this might be actually x dot. So point is, this m is a big expression, but at the end of the day, or at the end of the simplification, you're trying to explain that x double dot equal to kp times some expression into x, and the reason we are doing this is to explain the concept of stability. Okay. So ultimately, you can see that we get into some sort of a matrix, and let's take one more minute to see how we are looking at it. So it seems like that matrix M or matrix L, that you get into a matrix L that has this kind of structure. And ultimately you will get into you look at eigenvalues of that matrix, and these eigenvalues will be useful for understanding the stability of the system. Okay, so I know it is a little more involved, and we will skip this, but for those who want to pursue in detail, there are few papers that I mentioned in this. So I think it's better to skip this to a little more than even what I thought. At the end of the day,
so the gamma what we got in plus and minus, both sides, we have to take only
yeah, it's like, right, but then it says for the stability of the system, the gamma has to be less than 0. So these are the conditions, for stability. So yeah, for the system to be stable, lambda has to be less than 0. That's what this says. So that means the real part only. It could be that we get into complex values here. Right. Yeah. Actually, it became a little more in terms of even explanation. Also, it becomes a little more complicated, and so. But I just wanted to bring up. Yeah. Right. Yeah. Right. You get into ultimately you're simplifying everything into. You start like this. Start with this model, and then ultimately you focus on the matrix M and L. L is the matrix actually. Here, yeah, that's supposed to be x dot. Yeah.
So if we know the position and velocity, we should be able to justify either repulsion or
right. Yeah, I mean you have the
relative speeds and relative distance. We should be able to justify.
Right. Yeah. So the ultimate, I think basically we're trying to relate whether it is stability or time it takes to convert in terms of the network topology. So if this is simulated, yeah, this is the simulation setup. Again, let's review this quickly. When you see, by the way, one thing is we are considering only two-dimensional model. It's not 3D. It's only considered x and y. Like a player, we are ignoring z actually. That means the altitude is kind of fixed. We're not even considering it. So which means that there's a room for doing a three-dimensional model of this if someone is interested. So here the desired velocity is some units, nothing, no specific units are mentioned. Let's consider x velocity is 7 and y velocity is -6. And what is meant by time constant? You are moving at the steps of 0.08 seconds. That means iteration 1 to 2, the delta t time difference is this. Collision zone you defined as r dash equal to 1. Now, if you let's go back quickly to see what is r dash. R is the small, r dash is the large. So r dash is the collision radius. So collision radius is 1. Even though we are using small r or just r equal to 0.4, but that r dash is being used in the model. R is not being used. So basically, why are you using r? It's like it's a dangerous zone. Basically, R you can never. Basically, we are trying to say we cannot get into below 0.4.
So that is the size of drone.
Yeah, that's the size of potentially size of the drone. We want to make sure that the all other nodes are
Should not come closer to it.
closer to point. Yeah, if the node is below 1, that you want to push it away. And a capital R equal to 5. So interaction zone is 5. So obviously for doing simulations, you have to come up with some numbers. And some constants are defined. Now you can see that.
Communication rate.
Right, you're right. In terms of desired geometry, if you need to first come up with the graph. You need to come up with the graph, and then these are relative values. Now, for example, one of them have to be fixed, of course. In terms, when you come up with the relative values, one of them have to be fixed. And these are relative to the one. I think one is the leader. You're saying one is the leader. The position is fixed, and these are relative positions.
Symbol coordinates.
Say again.
The position coordinates of
Position coordinates. In fact, relative positions.
Distance.
Yeah, relative distances. Yeah, distances. You're right. So, for example, if we fix one, let's say one is fixed, then you are finding the distance between the two. Yeah. Not absolute. I think that's the main idea. And these colors are x is the initial location, and y is the final position. So what we're trying to answer is, if you start at any random location, you can place them initially anywhere, and we want to get this desired geometry. So the question is, starting from random locations, how long does it take to form into this pattern? That is what we are trying to say.
So these are relative to leader or relative to adjacent?
Yeah, so one of them have to fix, that means leader position is fixed. So let's say one is our leader, okay? Then these are the distances. So let's say node 1 is fixed. That means 1.1 and 1.3 are fixed, and then this is relative to this, and this is relative to again 1, yeah. Relative to the leader, I think. All these are related to the leader.
final question is the convergence of nodes as per the required.
Say again?
So final position is all about our achievement of convergence of all our nodes as per our.
Right. This is the requirement. Okay.
After movement of that distance itself, we are getting into the final position.
Right. This is the initial position, and we want this pattern. This is the desired position. So it's possible from this graph. It looks like that it might be happening somewhere in the middle, but obviously you need to figure out what is the error, right? Now, this is a desired positions, desired geometry rather. Then at each instant you're trying to see how much is the error, and based on the error threshold, you define whether you reach the consensus or not. Okay. Here is some interesting results. I'll describe briefly. This graph is without collision avoidance strategy, meaning that there are two things we are considering. One is repulsive force and consensus force. So what the graphs are showing you two results, and in one scenario we are not using the repulsive force. That means without collision avoidance. You are using only consensus force. What is the idea of consensus force? You want to make sure that they are within the communication zone. Communication refers to, again, the connectivity, right? So if you want to maintain the connectivity, basically one of the goals is to maintain the connectivity. The second goal is to avoid the collision. So yeah, here we are trying to say, suppose you don't use the repulsive force, then what happens? And the other graph is, next graph is with collision avoidance. So if you don't intentionally include the collision avoidance strategy, then it's potentially the two nodes can come so close. Okay, for example, in this example, they are starting at some in the beginning at time equal to 0 or iteration 0. These are the positions. They are different positions, and you are trying to get into this pattern. This is the convergence, right? And then in between, as you increase the iterations, there are some scenarios, some locations where you maybe collide, especially in things like we focus on one aspect, a pair of nodes, agent 3 and agent 1, I believe. So these are the XY. Yeah, this is only the distance. You are plotting the distance, but here we are giving the coordinates. Second.
Coordinates are the iterations and the distance.
Right. As you increase the iterations, how are you? So the main idea is, the main point here is, if you don't include the collision avoidance strategy or repulsive force, it's possible that you're trying to get to the pattern, but while trying to arrive at the pattern, in between you may be colliding. So that's what this is showing you. In fact, the improvement, I mean, look at the values, x equal to 15 and then y equal to some 0.666. This is another scenario, I believe. There are two examples. We'll look at two examples. Two simulations rather, okay? Two different simulations. Same concept, you're trying to do in two times. And then with collision avoidance, with collision avoidance strategy, collision avoidance included, you can see that the distance is, look at the distance, x equal to 12 and y equal to 0.05084, and then in the second case basically you are highlighting that particular location. In fact, these numbers are that critical, but we just wanted to show the actual location. The key thing is the comparison between this and the previous. I think we need to focus on that. Yeah. So if you look at this graph and the next graph, with collision avoidance included, you see that the tracks are little bit distant. So track, for example, for the track corresponding to agent 4, just focus on the two tracks. Look at the two tracks and see these two are little bit separated or more separated compared to the scenario when you're not including collision avoidance. So basically the tracks are a bit more separated when you include the repulsive force to avoid the collision, as opposed to the scenario when, these two tracks are more separated compared to the scenario when you are not including the collision. So that's the main point here. The reason we are showing these numbers are just to show, to compare numerically, or we know what is the actual location. But this is not important. In fact, don't focus on these numbers. Focus on the tracks. The tracks are closer without collision avoidance. The tracks are a bit far when you actually implemented collision avoidance. The idea here is that while consensus building is focusing on, or consensus force is focusing on bringing the nodes closer to maintain the connectivity, but collision avoidance strategy will make sure that they are separated enough. So that is the main contribution that we brought. Okay. Really speaking, that is what I wanted to convey.
Separation distance is always greater than r equal to 1 unit. There will be no collision.
Yeah, separation has to be
Greater than 1 unit.
greater
The
than
assumption
1.
which we have taken.
Yeah. Let's review that once again.
It's like
Yeah, it is. Yeah, if you're right. If the separation is
r dash.
from any node to any node, okay?
Yes.
So focus on node 1. So if you focus on node 1, any node that is, so for example, node 1 is here. Physically, node 2 and 6 are closer. We want them to be closer. But at the same time, you want them to be here, not in the red circle, right? So we are applying two forces. One is the repulsive force to push them away from here into this region, and the attractive force or collision or the consensus force is trying to bring them, if they are outside this, they want to bring them inside. So that's kind of, that's the reason we have two forces. So I think the entire model is the vertical, whether the model works or not depends on how accurately you are modeling the idea, the concepts of repulsive force and attractive force. Number one. Number two is as long as you include the everything. If you do model accurately, that means if you don't make any mistakes in the modeling, you're supposed to see the effect of both forces, bringing them closer for connectivity point of view, and then separating them when they are causing some potential collision. And so the graphs will, all this is done in MATLAB. All this is done in MATLAB, and then if you see that the tracks are not so close, then you know that your model is working. Yeah.
Two tracks they are having different, three tracks they are having different, one track they are having rails.
Can you repeat?
If you see the tracks,
Hmm.
two are having dips that monotonically decaying and it is reaching to
Oh, yeah.
larger deviation. Whereas the first one, the blue color one, it is having a spike kind.
Okay, you're saying why this is, right? So what's happening is like this. These vehicles are at random locations, and they're trying to reach the desired location, right? And notice this. D1J stands for distance between.
Leader and the jet.
Leader is one.
And jet node is
Yeah. So to begin with, you're only looking at there are how many? Yeah, 5 agents. There are 5 agents.
leader 1 is agent 1.
Yeah, leader 1 is agent.
4 agents.
Right. These 4 are the 4 different nodes, distances of each of the node with respect to 1. So let's look at the blue node just to understand. Just look at the blue. The blue node is in the beginning at a distance of some 4 point something, and then your question is why it is increasing and decreasing. So because each node is working separately. Node 1 is the leader. Okay, let's keep aside. But node 2 is trying to come into the place, and it should it based on this graph, this topology, it has connectivity with 3 and 1. So it is getting the what you call control input based on the information it is gathering from node 3 and 1. So it is possible that the distances with respect to 1 can go up and down because every node may not be connected to node 1. So it is gathering information from its own neighbors. So basically the dynamics are dependent on which nodes you are connected to. So for example, let's say here we are focusing on the distance between node 1 and node 2, but node 2 may not be connected to node 1. Node 2 is only getting information from its own neighbors. So it's some sort of a distributed operation. It's not like a centralized information gathering and processing, but each node is getting information from its own neighbors. So it's possible that since you are looking at with respect to 1, yeah, it's possible that you may not see monotonously decreasing.
So let us assume that there are 2 neighbors who are equidistant, right? And one node is moving away and one node is closing back. You get that pattern. Right? I think you can see that there
Right.
is a decrease and one is increasing. So you get one dip and one increase. Right? That can be one connection because they are randomly placed. Again, you run it, you might get a different pattern.
Yeah, it's interesting to see the dynamics actually. It's a good observation because it's like each look, this is the important thing. Each node is looking from its own perspective. It's not looking at it globally. Each node is looking at its own perspective. But at the end of the day, the information that you are getting is somehow aggregated. For example, I think
you're not putting collision avoidance.
Yeah.
If you put collision avoidance, you can keep that distance. It is not that it might be coming closer and it might be closer. And after some time, again it might go.
Yeah, so the dynamics are, like node 1 is pushing away, like if node 1 neighbors are 2 and 6. What it's doing is, in this algorithm, the control law is implemented on individual nodes, right? So node 1 is looking at, I want node 2 and 6 to be closer. It's trying to maintain the separation as well as closeness with respect to this. But then when you go to 2 is trying to maintain proximity to 1 and 3, right? But node 1 is not concerned about 3 at all. So node 1 is focusing on its own neighbors. Node 2 is focusing on its own neighbors 3 and 1, and node 3 is focusing on 2 and 4. So everybody has their own set of guidelines, everybody is gathering information based on the neighbors and is trying to maintain the relative distance with respect to their own neighbors. But by doing so, like for example, I think we had a lot of discussion when we are working on this, how things actually working. So node 1 is maybe pushing node 2 away if they are coming closer, or trying to bring closer when it is going away, based on the guidelines we have. But immediately when you run the same algorithm on node 2 says, okay, I need to bring node 1 closer, or the other way actually. Node 2 says I need to maintain the distance that is dictated by, that we defined by the prior what you call the geometry. So node 2 moves in such a way that it is maintaining the distance, the required distance, right? So earlier node 1 is trying to maintain the distance, and now node 2 is moving according to the design pattern, and then node 3 is moving. So when you go through like a cycle, like a round robin, then each one is trying to maintain its own position. So by doing so, it may be moving closer to one sometimes, or maybe moving away. Yeah, I hope it's still a little bit confusing, but I hope is the point. So we are trying to say We are going from 1 to 2 to 3, 4 and 5 one by one, and each node is trying to move in such a way that it maintains the relative position with respect to its neighbors. So in that sense, node 1, when the control law is applied, is trying to maintain its own position with respect to 2 and 6. And when you go to 2, it's possible that 1 is trying to come closer, but 2 is trying to be closer to 3. And when you come back to 1 again, that 1 is trying to go closer to 2, but node 2 may be going closer to 3. So the dynamics are kind of distributed, and ultimately it is equivalent to as if you're having centralized control. So it's a distributed system, but ultimately it is equivalent to a centralized system. And I think but it's a very interesting problem because the theoretical development or theoretical model says that it predicts how much time it takes and how many iterations does it take, and it seems that whatever expectations we had from theoretical model, you can also see in the form of results.
One last question. In convergence, our leader node is S1, and all the other remaining nodes, the followers should be within the interaction zone of S1, or they can communicate through a hop-to-hop, like if S2 is within the interaction, S3 can connect from external.
Right. They don't have to be closer to, all nodes don't have to be closer to 1. The closeness depends on the geometry we define, right? So with respect to 1, or according to the geometry, node 2 has to be connected to node 1. Same thing with S6 connected to node 1. So S1 is only looking at only its own neighbors, and it makes sure that node 1 will move in such a way that it is closer to, it maintains the relative distance with respect to S2 and S6 only. That's exactly what we are referring to. The reason why you are saying that these are all like going up and down, because we are only looking at the distance with respect to 1, right? Again, these two are not matching. This is something random I drew. But if you look at this, what we are trying to do here is that that node 1 is moving. Node 1 is trying to move in such a way that it's maintaining the relative distance between 2 and 6, and 2 is trying to do the same with respect to 3 and 1. So that's the reason. If all of the nodes are trying to be closer to 1, it's a different issue. But we are doing completely in a distributed manner. So while node 1 is trying to be closer to 2 and 3, node 2 may be moving when node 2 may be moving away from 1 because it's trying to get closer to 3. I think, but the point is, it's not like all the nodes are trying to be closer to 1. Only the neighboring nodes.
So does that mean for S3, S2 is the leader node?
Not really.
S1, the graph is for S1 only. You can see that yellow line and purple line are closer to 1, T1, and blue and brown is far away from 1. Okay, but all are maintaining the same.
So all the nodes.
There's only one leader. There's only one leader, which is
And we are
1.
measuring with respect to that.
Yeah.
And you can see that you can put that blue and brown at the second half network. And you can keep yellow and violet at first half network.
Yeah.
So in traction zone we can decide, but how we decide the collision zone, that how much we will take the collision zone?
This actually we need to come up with our own way of defining how much is a collision. But in this case, we simply just like we use unit 1, right? 1 means, just for simplicity, we said unit 1. But the actual safety distance or communication distance depend on communication zone or interaction zone and collision zone depend on, for example, I think Dr. Sai Prakash mentioned, for collision zone you need to consider the vehicle size. And for the communication zone, it depends on the transmit power and how much communication range. We talked about that briefly yesterday. Nothing is fixed, right? Depending on
communicating radius and sensing radius, like network same radius.
Right. Now here we're not considering sensing zone, but we're saying communication zone and collision zone, right? So what do you mean by communication? It's a communication range. So that depends on how do you set it up. You know, how much basically how much, what's the communication range you want. That's variable. That depends on your application. But for simplicity's sake, we're just calling it as what. R dash equal to 1, and this I think in the simulation, I think we put the number.
I have some question.
Yeah, we use just 5 units. This for now it's a simulation, right? We just use a random number. But something logical, you know, it should make sense. For example, collision zone is smaller compared to interaction zone or communication zone.
In interaction zone, it would be that we will decide the dimension, then that only dimension we want to fly within the unit. That would be interacting in interaction zone. But how we decide the collision zone, that how much
It's more like a safety distance, you know. How much separation you want to maintain, minimum separation between two vehicles. Right? You know, it's both like a safety. You know, what's the safety criteria? How can you assure safety of a vehicle? So based on that, you need to define. So for example, yesterday in our what we call corridors and all that, in that discussion, we defined safety distance like to be 200 meters. But nothing is set in stone. It depends on the vehicle size. If the vehicle is very big vehicle, then you want to maintain more separation. Yeah, but these are some examples. Nothing is based on any practicality. It's more like a simulation. Yeah, I hope you have get some idea about the problem. And then while this kind of simulations can be done, but the foundation is basically the matrix theory, the algebra, plus there are some ideas about how to implement this repulsive force. How do you model a repulsive force? We didn't discuss in detail, but something like, you know, like potential force. How do you come up with a simple function that describes the repulsion? So repulsion means it should be controllable. You know, you're saying it's a function of some parameter, and based on if you increase the parameter, maybe you should increase the distance, and if you reduce the parameter, it should come closer. So some of those things are like, you know, basically they depends on some physics models, or models that borrowed from physics.
that's the how the equation depends on the eigenvalue. So actually there is any relation or something.
See, okay, the question is how come the sum of this consensus building aspects depend on the eigenvalues, right? Yeah, that's a kind of interesting, you know. So as far as me and my students are concerned, we came to know through literature only, you know. But our first thing is okay, and the literature says, yeah, consensus problem or consensus time or convergence time depends on the eigenvalue. That's our first understanding of this, or first knowledge. But then you have to do our own study in terms of asking or convincing ourselves why is the case. Yeah, you know, I think that somehow we have to get convinced why is the case. But what we are trying to do is, my interest is why second, you know, why not first and why not third. So, but in general, the answer is the eigen structure. It's also called spectrum. Eigenvalues tell us a lot more information about the topology. But in general, you know, given a matrix, yeah, eigenvalues tell a lot of information about the matrix, right? So here our matrix is nothing but the topology, And the topology is based on the structure of the graph. So basically it's telling us the structure. Structure means connectivity. In terms of networking, it is a connectivity. And obviously, in some sense, the more connected you are, the more information you are able to gather, right? So how information is flowing, that is captured through the topology. So probably I'm not giving you an answer to exactly your question about how eigenvalues are telling all this information, but in general, once you are representing the topology in the form of a matrix, and matrix properties are well captured by the eigenvalues.
Eigenvalue tells about the stability.
Okay.
Constraints
We're talking about consensus. Yeah. Consensus also in some sense is connected to stability. For example, it refers to something called like balance. If the network is balanced, like for example, take a regular graph, or fully connected graph. If the graph is fully connected, really speaking, in one step you can answer the convergence, right? So maybe you can think about like this. What is the max? There's something called maximum length. Like how many steps does it take to what's the maximum number of steps that it takes for each node to reach every other node? So like a multi-hop, how many hops does it take to reach, for example, to reach all nodes, right? So that depends on the connectivity, and then that is connected to degree. So in some sense, just like the way you said, stability depends on eigenvalues, the same way eigenvalues also capture the distances from one node to another node. In fact, again, my answer is not exactly clear, but basically, the moment you are designing a matrix or capturing the problem in terms of matrix, then eigenvalues will provide a lot of information. In fact, sometimes I wonder, since childhood we learn about eigenvalues, right? But there is so much of meaning, so much of value that eigenvalues provide. And here is an example. All right, I think that's good for now. We'll see tomorrow. In the afternoon, Dr. Sai Prakash is going to get into some lab.
One small doubt, sir. So, does all the relative positions of the individual zones they are related to the leader node or the neighbor node, sir?
Only the leader node.
Only the leader.
Yeah, all the relative positions are with respect to the leader.
So how does the node S3 know that S2 is its neighbor before coming?
No, actually, no, to begin with, all the relative positions are. Okay, I think I see your point. The relative positions are with respect to hang on. Okay, I think what you're saying is, to begin with, we pose the problem as, these are the relative positions I need with respect to node 1 with the leader. But when you actually define the geometry or the control law for a specific node, then you are only dealing with the neighbors. So the point, I think it's a good point. What you are asking is, how do you know about all the nodes? You don't need to know all the nodes. In fact, that's the interesting part of this. When you are looking at node 1, you're only working with your neighbors. Okay. So the positions and the desired positions and all those things are related to only the neighbors nodes. So in the equations, at every node I, for example, you only need information, you only get the information, and you only need the information of neighbors. You don't need to know the rest of the. So understood, right? But generally, when you pose the problem, you need to give relative positions of all the nodes to begin with. But when you are implementing an algorithm or a process at a specific node, you're only using the information of your neighbors.
So do all the neighbors know who is the neighbor?
Yeah.
Okay.
How do you know? We are actually assuming that they're all talking. Okay, they're communicating. But it's a good observation. That's the reason I'm from the beginning I was saying it's a distributed problem. It's not then you're not solving it. There's no centralized controller. It's purely distributed. So in this case, node 1 is only connected to node 2 and node 6. It is not aware of others. But node 2 is aware of node 3, right? In some sense, you're running or implementing the algorithm at each node, right? So node 1 is operating from its neighbors in gathering information from these two, and node 2 is gathering information from 3 and 2, node 3 and 1. So at the end of the day, you're going to come back to 1, right?
Yeah.
So somehow the information is flowing. So one interesting question here is, depending on the application, you're doing different things. For example, if you're finding an average of values, you're doing some computation at the average computation. But here you're trying to maintain the what you call separation or closeness. So one interesting question is, irrespective of what exactly you are doing, whether you are doing you're computing average value or trying to maintain the distance, the interesting point is that the number of steps it takes to compute the average or the number of steps it takes to converge to the desired location, both of them are dependent on the eigenvalues. So that's the interesting point. It doesn't matter what you do, what computations you are doing or what actions you are doing, but inherently the number of steps it takes to achieve consensus is a function of, it depends on the topology and in turn the eigenstructure. So that is somewhat fascinating.
And the leader's formula S1J. So we are going to take J equal to only 2 and 6 for that.
That's correct. Yeah. So remember we say J belonging to neighborhood.
Right. So
J belonging to neighborhood set of I.
Similarly, for followers, we were mentioning S of ij. So I refers to that 2 or 3 which he was talking about, and J belongs to their neighbor set.
Yeah, I is the
node which we are talking about.
Which we are referring to, and J is all the neighbors. Okay. For leader, we say I equal to 1. Yes. So we fix. Yeah, I think you got the point. So the big thing is, in the beginning I was showing you some results of eigenvalues and all that, right? So that's for static network. So for mobile network, how things behave, how things happen, what is the impact of mobility. So that is kind of a good research topic. I had some papers on that already, but basically we were trying to see what is the impact of mobility on consensus building. I mean, there's a lot more to talk. For example, like this is one rule. Okay, when so let's say because of mobility you lose connection. So then what happens? If a node is isolated, then you cannot reach consensus. That's a known rule. If you look at for example, if you look at the adjacency matrix or Laplacian, if the node is disconnected, there is no way to share information. But what happens is, think of in the next instant, the node again gets connected. Okay. So just like the flock of birds, what happens? A bird will get away and connect with something else. So what is happening? For some time, the node is disconnected. The bird is disconnected with the network, but it's again joined. So the way to look at a mobile network is that you can come up with at that instant, what is the graph? Next instant, what is the other graph? So basically you come up with a series of graphs And then the thumb rule is, the consensus rule is, as long as you are connected to the network at some point, you don't have to be connected all the time. As long as you are connected at least sometimes, then you can assure that you can reach consensus. It takes a long time, but you can still reach consensus. So just because you lost the connection doesn't mean that the whole thing is out. You can still reach consensus. So what they do is, in that scenario, they come up with a series of a sequence of graphs that represent instant graphs, or graphs represent the topology at different times, and then you can take the union of the graphs. As long as the union of the graphs is connected, you're good. So then you do the analysis of the eigenvalue analysis of the union of the graphs. So what do you mean by union of the graph? You create a set of graphs, and each graph is on its own is not fully connected or not connected. There may be isolated node here and there, but as long as the union of the graphs is connected, you're good. That's an interesting result of again consensus building. So, but still, it's understanding mobility and understanding the impact of the mobility is a research problem. That's a challenging problem. Let's stop here, okay?
So even packet losses and packet drops will be considered as similar situation.
You're referring to this. You're saying that S1 is always connected to 2 and 6, but that may not be the case. What is the impact of packet losses or basically communication losses in general is something. There are some papers around that. Okay, so consensus building in uncertain scenarios, meaning that what happens if your link is lost. So, but for now we are assuming that in this case, like every node is always connected to the neighbors. Like for example, you are saying S1 is always connected to 2 and 6, but that might not be the case. In the model also, so we are saying, I think as Durga Prasad observed, there is a J belong to Ni, which means that you are saying all J's that belong to neighbors of I, set of neighbors of I. But what if one neighbor is not connected? Then you lose the information. Okay, why do you need to be connected? You need to know the position of the neighbor. But if you're not connected, you won't get the information. So then obviously the model doesn't work as we expected. But there were some articles that talk about those uncertainties. Even this is not easy to follow, right? At least the model, even though I tried my best to explain the summary and the gist, it's not easy to get it in the first instant. But think about those issues.
But actually, the detailed one algorithm, DSR algorithm, explain how to get connectivity, how to use connectivity. These things are yet to work.
Right, yeah, wonderful, yes.
So take S2 as a node and S1 and S3 are neighbors. So suppose, just for assumption, we lose S3. So is S2 smart enough to accept S4 as its new neighbor, or like how does that work?
These nodes comes up and goes down.
Connection
It
is
not
not
static.
Right. So each
They are not static.
they're not static.
And they do it in a continuous fashion. It is not that periodically after 1 hour they come. It's continuous management. Not good.
Yeah, at least in this model, we are assuming that you are not losing if the nodes are adjacent, we are assuming that the nodes are adjacent all the time. Okay, meaning that may not be physically, but somehow you are getting the information. But if not, the model fails.
As well, in the exemptions I have defined more than everybody is listening and everybody is cooperative with sending the messages.
It's a static topology.
No, it is not
No,
static.
it's not.
Then new neighbors addition.
Yeah, they come in and they go.
So like add
You have request. I told you our request and our for and how they come in, how they go. Error, if there is error, how to handle it.
Yes,
I think I have
Yeah.
definitely DSR algorithm, how they come and how they go about. There is a request packet which will be transmitted, and there is a response reply from the request. Based on that, their output will be generated. These things are constant. They are not like static and all. They are dynamical. And I think we have a lab session on DSR and AOD. And they walk also random. It is not that they follow a straight line. We have random walk models where they walk randomly and still the network is formed.
So in this context, actually, we came up with some notion like logical neighbors and physical neighbors. You know? So logical neighbors is, so even though node 2 is maybe not, sometimes it may lose a connection, but what you're saying is I need the information from S2. So to do that, probably that Sai Prakash is mentioning, if node 2 is somehow lost connection, then you are expecting the information from node 2 from some other nodes. So that's why it is like a logical neighbor. Okay. So
every node have a cache. They know the alternatives. It is not that they find right now. When I am finding a route to you, all the others also know how I am going through. So they know the logical routes. When this link is lost, they reach like that. They need not have to find route again. In the cache, it is available. These are available in the cache. They can use that and still be.
Correct. So this topic is complete, and then again you can find the papers.
Can you like that set one?
Yeah. No, it's fine. I think it's not completed. It's correct.
Communication. And actually this talk is split into two parts. One is short range and other is long range communications. So for example, when we say short term or short range communication, the range is very short. It will be in few meters or tens of meters, not more than that. So then why it is so important for us to deal it with when we are trying to speak about autonomous vehicles which are flying and so on, where the minimum distance will be at least 100 to 200 or 500 kilometers away or 1 kilometer away and so on. But we also have to understand that the drones, when we try to take, there are number of internal components which we have to check whether they are functioning properly or not. For example, if you have a 4-quadrant type of fans and they are moving, one of the fan is not functioning. At least we should know that it is not functioning. And the drone has to communicate that information. So the fans have to communicate to the central processor of the drone. And the drone has to inform the base station or something so that some necessary action can be taken up. So it is not that only long range communication is required from drone to drone or drone to base station. we also require short range communication stuff where the parts of the drone try to communicate among themselves for the functionality of various components. So in that context, we are trying to look into it. So if we try to look from the communication engineer point of view, we have only one parameter is the range. How far it can communicate, whether it is whatever technology it is, what is the limitation of that communication plays an important role. And the bandwidth, the second one is bandwidth. So how much bandwidth we can have for different communication technologies available to us. So if we have some idea about it, we will be able to pick up a right technology for the right purpose, right? So in this context, if you try to see, we have segregated into three parts. One is short range and other is mid range. In the mid range, we have divided into two classes, mid and long range. We have classified into two parts. One is licensed part and other one is unlicensed part, right? So in the case of licensed part, you have to pay some money for usage of the communication. In the case of the unlicensed part, you need not have to pay anything, you can use it. Like for example, Wi-Fi is an unlicensed spectrum, you don't pay for it, right? Bluetooth, it is unlicensed spectrum where you don't pay for it. So the mid-range and the long range can be segregated into two parts. One is licensed part, other one is unlicensed part. And in the short range, there is no licensed part at all. All are unlicensed only. Okay? So if you try to see closely, we are more used for Bluetooth and the Wi-Fi, right? Regularly we try to see the words like Bluetooth and Wi-Fi in the short range, which means that those two try to use a frequency which is unlicensed spectrum. For example, in India we have ISM band, which is 2.4 gigahertz band, which is unlicensed. And now recently 5 gigahertz we have one band, which is also opened as unlicensed band. So if you design something in that frequency band, you can freely use it. But there is a limitation on the power you try to transmit, right? You cannot transmit whatever power you want. There is a government restriction that you have to use 0.1 watt or a half a watt or quarter a watt, so that your distance is limited to only 10 feet or 20 feet or 30 feet and so on, right? You cannot go beyond it, which means that you are entering into some other communication range, some other person who is using the same frequency and you are trying to disturb them, right? That's the main reason the government has told that you can use this frequency free of cost with a limited power to it, right? So the power has limited it, and generally we say that they are only for short distance, right? And we have for mid-range and long range, if you try to see, we have various technologies available to us, and they fall under different categories. So coming to a bigger picture, dividing it into some more sub-blocks and trying to venture into it, the first one is NFC. I think this is very popular nowadays. You get a cards which you do not have to swipe, just go near it, automatically the billing will be done. So that is what we call it as near field communication. They use electromagnetic signal to interact between the device and your card, right? So even if somebody brings a device near to your pocket, it gets cut. So you have to be very careful while using your NFC cards also. So best way is you again put some OTP or something pin on it and then try to activate it, right? So be careful, like NFC, if it is activated, even if you don't know also, somebody brings the machine near to you, it gets activated, right? So it is within a 1 meter, means 3 feet. Okay, 1 meter is 3 feet. So near to 1 or 2 feet, if somebody moves with your, what is that machine? Yeah, if you go along with it, your money will be get cut. Okay, so it's not only for the cash transactions and all. This is very useful if you try to see, like for example, if you are trying to enter into a room and all, you can just show the card and enter into the room. Otherwise, the room will be locked, right? There are multiple applications for that. It doesn't mean that we cannot use it for drone communication. Even drones also can be activated using NFCs, right? So you can activate the drone, but it will not start until it gets a signal from NFC. So most of the cases we try to use for security purposes and all. Then we have RFID, and this is again a short distance or short range communication purpose only. It can activate up to 2 meters and so on. So nowadays, if you try to see most of the applications, like for example, the animals and all, they are given with tags, right? And those tags will help us in understanding the health of the animal and where they have been moving around and so on. So the RF, when they enter into the farm, there is a RF radar which tells how many are there inside and how many are outside, or where exactly they are roaming. And even the health also can be monitored, like health of the animal can be. So it's not only that, even for clothes, even for if you go to mall, the things and all are RFID, you can just pick up and move around, right? So this is for short, very short distance. And preferably, we will not use such type of technologies on the drone, right? Because the range is very small. Then coming to the next set of modules, we have Wi-Fi, Bluetooth, Bluetooth low energy, Zigbee and Z-Wave. And mostly if you try to see, the Z-Wave is not that popular in Indian segment, whereas Z-Wave is popular in US, right? So we'll try to see what actually is the difference between these two technologies, the Bluetooth and Wi-Fi, which are popularly used. But nowadays, please assume that the Bluetooth, we don't have the energy consuming Bluetooth. We have low energy consuming Bluetooth only, where the energy consumed by the Bluetooth will be as minimum as possible, right? So this is the next segment, which can run up to a few tens of meters, not only 10, 20, 30, 40, 50, and so on, right? But it cannot go beyond 100 meters. Right, the maximum thing is you can obtain is 100 meters if it is not having too many obstacles and all these things. Multi-part, if you have many obstacles, because when the signal transmits, it gets either reflected or refracted or scattered. So too many reflections or refractions will try to spoil the signal, otherwise you can communicate. And these two are potential candidates for getting the information inside the drone. For example, when you have a laptop, if you activate the Bluetooth, you can connect your printer, your pad, your mouse, your headphone, and so on. Similarly, you can also connect most of the components of drone to that. And we'll see how the drone components are connected to that. And then we have another segment called a licensed and unlicensed segment, where you can buy the spectrum and try to use for your application, or the unlicensed spectrum also is available for you, okay? And the third one is, which is very popularly used, is cellular. And the cellular also comes under licensed. It is not like unlicensed spectrum, it is also licensed. But please remember that we have different types of networks, like it can be a metropolitan area network, or it can be a wide area network, or it can be an intercontinental network and all. So when you are trying to expand the WAN, the cellular will find more advantages than having the other, right? So when the communication ranges are increasing and increasing, better to go for a licensed spectrum rather than going for unlicensed, because they don't mix up. If you are trying to use the unlicensed spectrum, use at the last leg of the wireless. Let the other part of the wireless be handled by somebody, okay? So in the licensed spectrum, if you try to see, you have LTE-M, EC, GSM, NB-IoT. These are the three technologies which are popularly used. And now in the 5G networks, if you try to see, these three are integrated into it. They are not separate entities, right? You go to a 5G operator, ask him for LTE-M, they give you. If you go to a operator 5GSM, they have GSM. This is a very good technology. Like in case of 2G, 3G, and 4G, the infrastructure what it is there, they have not removed it, because the cost of installing and the cost of removing, if you try to see, it is more costlier than leaving it like that, right? So most of the things they leave it and go, right? So that infrastructure can be used for communication purpose, because they have been designed such a way that the frequency is at 900 megahertz. Right now we are trying to use 2.1 gigahertz and all. So as the frequency increases, the wavelength tries to decrease. And as the wavelength decreases, it cannot penetrate through the objects, because there is a relation between the length of the object and the wavelength, right? So if the wavelength is large, it can penetrate through the walls and it can go through it. Okay, so when the GSM 2G, if you are using 900 megahertz, it can go to a larger extent rather than just getting obstacles and all. Even if you have small obstacles, it can pass through it, because the length of the obstacle and the wavelength, if you try to see, the wave can penetrate, right? So this is one advantage which you can use it in the, if you are trying to use the existing GSM infrastructure for your communication purpose. And the narrowband IoT is another area where people are trying to use very small bands for communicating to the IoT device like drones and all, right? So these are under the license spectrum, and these are now a sub-component or sub-module of your 5G network. They are not separate entities. When 5G was not there, these are separate entities. Okay, so when 5G came in, they have been pushed into the 5G standard. Then coming to the unlicensed, we have MIOT, LoRa, and Sigfox. The Sigfox is not available in India. Only the LoRa is available in India. Otherwise, the Sigfox is a most popular standard in America, right? And most of the devices they have connected with Sigfox. And these two advantages, they can go up to tens of kilometers. So if you try to take a smart city, the city is around 5 kilometers radius, so 10 kilometers are covered. And if it goes by 10, 20 kilometers circle is, so all the city components will come into it, right? So the smart cities and all they are trying to do with this. At the same time, if you try to see our drone, they are only running at 1,000 feet or 1,000 meters and so on, so which is 1 kilometer, right? So 1 to 4 kilometers, you can easily use this technology. So these two are very competitive for us to use for devices to connect, which are autonomous in nature, which are flying below 2 kilometers or 3 kilometers. We can easily use these technologies, right? So we'll try to spend this one as a separate class. We have a long range communication class, and now we are trying to look at short range only, right? So this is actually the case study which has been presented in the Mahmood and Uday, and they have just given it in a different direction. The same thing, they have put it in a oval shape. So they have defined a PAN, personal area network, where it is very small, and they have the local area network, neighborhood area network, and a wide area. So they have used a different terminology to explain it, and they have listed out all the possibilities what they have. Proximity is very near 1 to 2 meters, RF and NFC and RFID, and if you try to see the personal area network, you have Bluetooth low energy, Zigbee, Thread, Z-Wave, and wireless HART, and the names, because what happens is when you try to look from a global point of view, each country started with their own standards, right? And if you go to Japan, they have the technology, China, they have the technology, and so on. So don't just confuse by these names, they are all used as a personal area. So we have only Bluetooth and Wi-Fi. We don't go for the other waveforms, right? So you have neighbor area network, they called it as, we call it as metropolitan area network, a town-like area which we are trying to connect it. And it is a mid-range, 5 to 10 kilometers radius, where the complete town or the city can be covered, right? And a wide area network where you have the same thing what we have mentioned, cellular and LTE, MC, 5G in the future, Sigfox, LoRa, Telensa, PTC, plus more, and so on, right? So these are the various technologies available in various countries, and if you boil down to our Indian scenario, you can only see Bluetooth and the Wi-Fi, and nowadays the Zigbee hotspots are coming up in malls and all where we can connect it, but mostly we are trying to see that most of the cases it is Wi-Fi only. So this is another same thing, they have tried to put it up. The soft.com people have just made a table for it. So that why we are trying to look at this more particularly is to know how much energy each communication technology consumes, because that plays an important role, because when we are in drones, we are driven by battery. We don't have a luxury of consuming it as fast as well. We have to use it very deliciously, and if you see Zigbee, it is medium type of consumption. If you can see here, there is red, yellow, green, and so on. The green shows that the consumption is very low, right? So we have some technologies like LoRaWAN and LTE-M and NB-IoT. They consume less power. So when we are using the autonomous vehicles, the energy has to be consumed as less as possible so that the life of the vehicle can be increased. That's the main aim of it. We want the vehicle to be for a longer duration. Right now, if you try to see the drones of defense and all, they have to fly around minimum of 450 to 700 kilometers to reach to the border, right? See, suppose I am operating from Delhi and I want to push the drone, it has to minimum cover 600, 700 kilometers to cross the border and go out, right? So such a long flight it should have, you can think of what is the battery size it required, because the motors have to run continuously, and the major element is motors only, right? So now, if I put more components on it, it consumes something more. So I have to minimize my power usage as much as possible so that the power will be available for the device to fly around. So in that case, if you try to see the LoRaWAN and the LTE-M and NB-IoT, which we call it as narrowband IoT, and LTE-M is long-term evolution mobile type of communication. So or cellular you can call, mobile or cellular. What happened? Yeah. So here if you try to see, they can be connected up to 10 to 15 kilometers. The height can be reached to connect to one of the drone, and from there you can give the message, instructions, and whereas here it is very small, meters only, LoRaWAN and so on. And the LoRaWAN is another good example, but the energy consumption is medium, it is not small. So what we try to do is, most of the cases the LoRa's if you try to take, we try to use for terrestrial network, where the supply can be given in a interval. Like for example, you have mobile, you can charge it once in a day or once in 2 days and so on. And if you keep GPS, it drains faster. So you can have to charge every day, right? So there are some components, because GPS is there continuously on the node, which tells us the locations. So there are some components which consumes energy. But still we have to see that the energy consumed in the autonomous device should be as minimum as possible. So this is one big usage, and these two are the next competent for that, and this gives a larger distance than this one, right? And if you try to take a 5G cellular, it goes up to 10 to 100 kilometers apart, but the only problem is the energy consumed a little bit more, which cannot be used directly on the mobile or the autonomous vehicle, because it drains very faster. So now, because of most of the cases people try to say that why can't the vehicles be connected with satellite or ground station and all, we can do it, but the only problem is this parameter. Okay, that has to tell you how long your device will be having life, or on the mid-drive only it will fall down, right? So the energy analysis of a vehicle is primarily, lot of importance is there to know whether the battery what is there is sufficient to reach to the destination or not. And it is same for your EV vehicles also. If you are driving a car, the electrical car, you should know when it will stop, right? If you charge it now, you know that it can go only to 70 kilometers. So before reaching 70, 60, you have to charge it again, right? So that analysis has to be there for drones also. It is not that drones are free from analysis. Energy analysis has to be done for drone, and that tells you how much the distance the drone can fly, and based on that you have to design your trajectory, right? Yeah. Yeah. So you can talk to your friend somewhere else in Hyderabad or Delhi. No, see, the 5G structure is something different. 5G doesn't have one frequency. The 5G has a band of frequencies where there is like a flexible fiber. Like what we say is, it can allocate to, if you see 5G, there are 3 different parameters in it. Latency is one, bandwidth is one, and the number of connections is one. So which one you are trying to look at is based on that. My RAN, radio access network, we call it as. The RANs are programmed such a way that depending on your requirement, I'll configure and give you. It is not that like GSM or something, there is a frequency, divide it, give it to users. It is not that concept. 5G has a different concept where the radio access network is a definable RANs. So even if you see 5G, there is a diagonal type of thing they'll give you, a triangle type of thing they'll give you with one latency, one bandwidth, one number of devices and all. So which direction you want to move, the RANs have to be programmed like that. Now we call it as open access RANs, ORANs. Earlier we have cloud LANs, free RANs and so on. The technology of RANs have been changed now. So based on the RANs, we try to allocate the user required facility. And now in 5G, there is an added advantage that you can ask the 5G supplier for a set of frequency spectrum, and you can use it for your private purpose, right? We call it as private 5G lands, right? Earlier we used to go for these lease lines, fiber cable and all. Those concepts have changed totally. In 6G you will see that the RAN's architecture have been changed totally, and the user can ask for anything and the supplier will give you everything, right? It is like a travel agent who will be sitting over there, and if you ask truck, he'll give you truck. If you ask a 20-wheeler truck, he'll provide you. If you ask a 4-wheeler one, he'll provide you. If you ask 2-wheeler, he'll give you. It is not like earlier, 4-wheelers, one travel agent, 2-wheelers, one travel agent, like that is gone now. It is the RANs are such a way, they have designed such a way that they have to accommodate multiple connections, like because the IoT devices are increasing day by day, and now we have crossed 50 billion devices, and we are expecting that it goes up to 80 billion devices, which means per square meter, if you try to take, it will be minimum of 10 to the power 6. That's the density we are trying to look at. So for that densities, the IoT devices have to be connected to network, and we cannot allocate bands to them, like multiplexing and all. There is a different type of environment for that. And at the same time, the house demands needs high bandwidth for having a 4K HD movie. And the other side, there is a robots operating, they need high latency where they have to perform, they cannot wait for 2 minutes to get an instruction. They have to do very fast because they cannot cut a patient and wait for the instruction. After that, sometimes they get into. So there are different requirements for the users, and the 5G network is designed in such a way that the radio access network will provide you all these things, right? You want a high definition video, and he wants only 1K, but the sensitivity should be immediate, like 4 robots are there, one robot sends and second robot, they should get the information. So based on the user requirements, the RANs are being classified. That's the concept. We were like, anyhow, I am coming back to the long range for the communication purpose. And I'll give you the spectrums what we try to use and all. And here also I will tell you Wi-Fi is now a potential base station for communication purpose. Right? In 5G, Wi-Fi 6 has came up standard where it is almost powerful as a base station, mobile base station. It is no more a Wi-Fi like this. Okay. So this slide only tells us an idea about the power. So that's why I brought in this slide. Okay, this is actually a very good example to tell us how the battery life is consumed in different technologies. Right? So don't assume that all the technologies will consume the same energy. They are different for different technologies. So now for the network connectivity, if we try to see, the most important parameter what we have to consider for these autonomous vehicles is the range. The range is the first one which decides what type of, how far we can communicate, and the data rate. These two are prime important for us. And then if you try to see the energy, right? Whenever we want to pick up a right technology for our vehicles to be connected and communicated and all, the first thing we have to see how much distance the device will fly and how long we can get connected. And the second one is the data rate, how much fast it can deliver the commands and get back the information. And the power, how much power it consumes. So if you can have an equation which connects these three together, it gives you a better idea of how the devices are working. And the third one is a frequency, which is again an important thing because we want a separate type of communication for autonomous vehicle. We don't want to mix up with other signals because the interference will start building up, right? We want something like a separate spectrum, like for example, if you try to see here, I think all of you hear FM radios, right? There is one channel called as 18.5 or 21.5 or 23.5 and all, right? So there are frequencies which are allocated to each station. So those stations will try to use that frequency to transmit. But there is an interesting thing in FM, if you try to see, all the bands are given 0.5. And why it is so? But anyhow, I'll just leave it to you all. You can just have a look onto the internet and get back the answer. It is not that difficult. Okay? So the next is security. And this plays an important role even for our autonomous vehicles because I might use a frequency to transmit to my vehicle, but there might be a hacker in between sitting and getting to know my information. And he will capture my data and he can put his data. So it is supposed to do something, but because of the hacker, it is doing something else, right? So I want security to build in because this plays an important role when you're in a distributed environment, right? And we don't know that is happening also, right? So these are some of the important things in our autonomous vehicles to be considered before we pick up a technology and before we are ready to communicate and transmit it, right? So these 5 parameters we have to somehow have a good understanding so that we can deploy our device safely. And this is from, and this is common for all the communication network engineers. And this is again a representation of various IoT connectivity standards. And please remember that when we say IoT, drone is also an Internet of Things only. There is nothing like it is separate and IoT is separate or not. Okay, anything is IoT only. Like a fan can be IoT, a projector can be IoT, a drone can be IoT, aeroplane can be IoT. So everything is IoT only. So if you try to see, we divide it in a cellular and a non-cellular fashion. You see, these are mostly it is licensed part and this is unlicensed part, most of the cases. But we have satellites which is again a licensed part. Okay, but it is non-cellular. It is, even though we say non-cellular, strictly speaking, it is cellular because they have a circle of communication over which only it can communicate. It cannot communicate in the neighborhoods, right? So here if you try to see the cellular, you have 2G, 3G, 4G, 5G. And now under the license, as I told you, LTE-M and BIoT is there. And in the non-cellular, you have Bluetooth, Zigbee, Z-Wave, Wi-Fi. This is another important thing which is now popularly becoming faster, Wi-Fi. Okay, Wi-Fi, Ethernet, or the wired we are not using anymore because wired is not suitable for autonomous vehicle. But it is still useful for internal communication, right? So under the unlicensed, you have LoRa, Sigfox, and others, and satellite we have VSAT. And this slide is primarily important for us to understand inner details of the technologies. If you try to see the NFCs and all the Bluetooth up to Sigfox, if you try to see, mostly these are all in meters only. Okay, most of the cases you can see that they are meters only. Coming to LoRaWAN, it is up to 20 kilometers they have specified, but mostly people trying to use experiments only up to 10 kilometers, right? And the NB-IoT and the Sigfox, they are, LoRa and Sigfox are very popular, but Sigfox is in American style because they have the ISM band something around, which is very popular around 868 megahertz, but we don't have that 868 as a free band for us, right? So we'll not be able to use that, but the LoRaWAN nowadays they have opened up for 2.4 gigahertz in India, so we are trying to use that. Even 433 and 915 also we are trying it for lab purposes, not outside, right? You get LoRa chips and all for 433 and 965 also, 868 also, but that is only for lab purpose. You cannot use it outside, right? So please remember that the LoRa is almost getting standardized, and mostly you can see nowadays people are trying to use it for smart dustbins, smart electricity poles, and smart meters also. Nowadays, I think within by the end of this year, all the houses will get smart electrical meters where you have to charge and use it, like your mobile phone. Okay, you pay before 100 rupees, consume whatever it is, again next you charge it, again use it. It is not like after usage you will not get billed, right? And I think mostly by the year end, every house will have smart meters, and the meter will not exist with you also. It will be in the distribution station only, right? It's only small box will be there in your house, which transfers the number of units to the place, and you will get it, right? So they are planning for LoRa connectivity and all. And if you try to see the maximum data rates, we are not so much interested for the operation of the autonomous vehicles. If you are using an application on top of it, for example, for communicating and setting up the network, you don't need any high bandwidths. Okay, so here actually when you try to see the drone technology and all, there are three parts actually. One is initialization part, the drones are made to fly, and then the network part, they are supposed to come to a stability, and then they are supposed to exchange the information and all. Okay, and then there is a termination stage. Once it comes down, it terminates. So the three phases if you try to see, the first phase is only for getting it to the required destination, and there they have to establish a network among the drones for the application purpose, and once the application is over, they have to come and terminate it, right? So you should see that the drones, when you are trying to send it, the time required for them to connect and form into a network should be as small as possible, which means that the number of messages you exchange for making the network ready for an application should be as small as possible. You should not consume all your energy for establishing a network. Then you are not left with a network, right? So when drones are left, they form a network. So that part should be as minimum as possible, which means that with minimum message exchange, you should form and set your network ready for a given application. Then the application runs on it. And once the application job is over, they have to come down and settle down. Okay, we call it as call establishment, call duration, call termination, right? So this process, we have to see that maximum energy is used for the application rather than you yourself setting up the application and finding out everything. should not be more consuming, right? So the setup phase should be consuming less energy. The application phase has to increase. So now the application is, for example, you are using a surveillance, you are using camera, it consumes more energy. Suppose you are only measuring temperature or humidity or something parameter, it consumes less energy, right? So the bandwidth requirement for a communication should be application dependent rather than some other, right? Whatever your application runs, you have to pick up that communication. And when you pick up that communication, then the energy is dependent on that. Okay? So please keep in mind that the energy analysis should have three parts: setup part, application part, and the termination part. So if you want more energy in application, you have to reduce the energy in setup and termination. Okay? So I run 100 iterations to make the network ready, might not be efficient way of doing it. But if it is minimum requirement, then it has to run. Okay, if a minimum of 100 iterations are required to set up a network, then you have to run. So how we do that? So we have an application dependent accuracies. Suppose, for example, you have a monitoring station in the air and you want to see that the application, even if the error is 1 degree, it is sufficient. So your iteration has to stop once it obtains the 1 degree, right? So we call it as application dependent services which we have to plan on top of it. Okay, but for defense it is 1 degree is too much, because if you think 1 degree, if I fire the gun and the space it takes 10 meters or 200 meters or 30 meters, you will miss the target. And so it depends on the application, what actually you are trying to look at, and that should tell what should be the number of rounds you have to do to obtain that accuracy. So now this is one important thing. The bandwidth plays an important role. Based on the application, you have to pick up which band it is, right? You are looking only for the distance 10 kilometers, but the KB is only 200 KB. The application, if you put a camera, it might not run, right? So please try to see that the bandwidths and your ranges should match, or you have to do some type of what we call it as you have to change the route of your message transmission. For example, I want to have a low power. For example, I picked up this NB-IoT, which is 10 kilometers I can get, but the bandwidth is only 204 kilobits, which I cannot transmit a video or a image, right? So what I do is I cut the image and send it through 4 paths, and the 4 we try to communicate now, right? So that type of techniques we have to use on top of it, so that you will not be losing much energy over the distance. Then we have the free bands. You can see the frequency bands given to us, and mostly if you try to see, we have 2.4 gigahertz is the free band. This is not a free band for us, and this doesn't matter to us because it only operates within 3 meters, right? So, but if you try to see the Bluetooth and the Wi-Fi and all, they are almost all the things are coming to 2.4, right? So now the 5G has been opened up, and now one more is coming up at G6G, and we'll see how the Wi-Fi is becoming popular nowadays. Okay, and as I told you, the power consumptions are also mentioned, and the standards are also there in place nowadays. Most of the communication technologies have been standardized by IEEE or some proprietary 3GPP or IEEE are trying to standardize it. And you can see the modulation scheme. There are different types of modulation schemes being used, like BPSK or QPSK or QAM and so on. And you have different types of multiplexing schemes, and the security algorithms are also in place. So in most of the cases, what we try to do is we take AES 128K encryption, which is very strong enough, and we use for most of the things, right? So if you have AES 128, they are almost secured only. Like for example, you take your Gmail, it works on 256, right? So this is because once we try to increase this one, the power consumption also increases. The number of bits are increasing. So the computation is also increasing. So please remember that. So 128 has found to be good on IoT devices like aerial networks and all. So this is a slide from slidingmotion.com. Actually, this is for the product demo and all, which I am trying to use it because it gives you some idea of what are the parts, main parts in the drone and so on. So you can see that this is the top view and this is the bottom view of the robo or the autonomous vehicle, and it has 12 important components around it, which plays an important role. Right? So this is one important thing which you have to give. The propeller, we should know whether it is working properly or not. Similarly, the brushless motors, if they are working or not. And we have battery to tell us how much energy is left. And you have a drone frames which has to be fixed up. And then the standard propeller is there, pusher propeller is there. There are two propellers for it. And motor mount is there, PDB is there, GPS module is there, flight controller is there, and this is transmitter and this is receiver, actually these two. And you have antennas, ASIC, and the landing gears and all these things. So why I kept it is, all these things, if they function properly, your drone is in good state. If any one is not working properly, then the drone has some problem and it has to be rectified immediately. So now what we try to do is, most of the cases, if it is a like a high-end drones, like for example military drones and all, we use a dual architecture. We'll keep it such a way that one fails the other, like aeroplane. When you sit in aeroplane, they are run by two engines. If one engine fails, other engine will take it up. It is not that they repair in the air and they come back. Right? Similarly, in drones also now we have improved to dual architectures where two sets will be there. So if one fails, the other one automatically will be picked up. We call it as fault tolerant designs, right? So whenever a fault is there, it has to pick up the second one as standby one and try to use it. So now what we are trying to do, this is the main flight controller, which is the receiver, and this is the transmitter. So this will be at the ground station rather than in the, and this is also required at the vehicle if you are doing bidirectional communication. Right? If you're not doing bidirectional communication, it is like delivery drones. You don't need a bidirectional communication. You program it such a way that it goes from this point to this point. Right? You don't need any instructions in between and all. But for some good application like what I'm saying, like military and all, we need to have the information from the drone saying that whether it is on the track or it has misled it or it has detected something, so that it has to take a course in the flight and all these things, right? So for that they have to communicate back also, right? Whenever you are planning for a bidirectional communication, you need transmitter and receiver sitting over there. So and there is a camera also attached to it to know the status of the coexistence, like when you are trying to look how far it is, you can get it, because nowadays drones are not only using for the tracking up and down and all, we also want to monitor whether the things are going right or wrong, right? And it's sometimes if you try to see, if like agriculture field, we want to monitor it, right? So there are the cameras are also there, and even if you try to see the agriculture drones and all, we have an extra tank fitted to it so that the chemical or some sprays are there inside which can spray it and come back. So there is a weight also included on it. So here weight is not shown. And if there is a weight included in it, the weight indicator has to be sent back. So this is the basic one. If you want to put some more top on it, like the warhead it has to carry. So again there is a weight coming into picture. So there is a necessity for doing some analysis on it, whether it can lift that much weight and it can reach to the destination with that weight, or it will drop it in between. Right? So this is only a basic one, which you can get it in the market for around 80 to 1 lakh, and you can use it for agriculture purpose and all, right? And this is from the slidingmotion.com. I have just copied it to see that various components can be displayed. So now coming to because as we have seen that most of the cases the Bluetooth and Wi-Fi is the short range, because we are trying to look from the short range point of view. I'll just concentrate on Wi-Fi and then we'll move on to the long range communication. So here if you try to see the frequencies which are unlicensed is 2.4 and 5 gigahertz. And around that frequency, you get a band of frequency. This is the center frequency. So if you try to see, you get a 20 megahertz band in case of 2.4, and it is around 120 megahertz in case of 5 gigahertz, which means that you have a larger band at 5G, and 2.4 you have a very small bandwidth. So you can use up to that, and if you want to use more and more, I told you like M has to be increased, or you go into OFDM so that you can accommodate more and more users. That's what we have seen yesterday, like if you QAM, 16 QAM or 32 QAM you can use, or OFDM you can use it, right? So this, by that what we can do is we can go up to 600 Mbps, or even with the latest technologies you can reach up to 1 gigahertz in the 5G band, right? So now once you have 1 GB bandwidth, it is similar to a mobile station, but still you can see that it is reaching above that also. So it is like a smartphone, compatible, affordable, well protected and controlled. You have a lot of security in Wi-Fi. Right now we are having WAP 2, but WAP 3 is also being started recently, and the security is, you can see that the power usage is more. You need a constant power on for the device, right? This is one drawback which Wi-Fi has. It cannot run on a battery. And sometimes the link comes, sometimes the link goes. This is again one drawback with autonomous vehicle. We want a constant link. We cannot say that link is not available, right? So now if you try to see the bandwidths what are there, you can see at 2.4 gigahertz you have 40 band, or total you can say 83.5 megahertz band. And at 5 gigahertz you have 580 megahertz, and now we are 6 gigahertz, it is 1200 megahertz bandwidth is available to us, right? 1200 megahertz means is 1 gigabit bandwidth is available, and now we on top of it, if you run 6 QAM or 16 QAM or 32 QAM or 64 QAM, you can see the bandwidth how much it has increased, right? So with this bandwidth, it is almost like a base station, right? Earlier we used to ask for 1 Mbps Wi-Fi line to your house, right? Suppose you get 10 Mbps, it is good enough. But now you have 1.2 gigahertz band, and it can be shared for 100 users or 200 users. So if 1 GB line is coming to you, means you can do a lot of things. So 1 GB you will not have data to transmit. So now what we are trying to do is in Wi-Fi 6, we are shifting it to top of the building. So if there are 10 families can use it. It is like a Pico station. Pico station is a small station which will be used in the mobile network. And hence, if you try to see your mobile calls, you might have seen that most of the times your calls are shifted to LTE or Wi-Fi and so on, right? Have you seen it? Your call has been shifted to Wi-Fi, which means that you are not talking to the base station, you are talking only to your Wi-Fi at your home, right? The call is initiated by mobile network, but it has been shifted to your Wi-Fi, which means that the mobile spectrum is still active for other users to use it, okay? So your calls are always routed through your, like your WhatsApp message. You call whomever you want, right? Which you are not supposed to pay anything, because you have shifted it to this. Why you have to pay it? For call initialization and all, you have to pay to the service provider. And hence nowadays you can see that they are giving you like 10 paisa call, 6 paisa call, 5 paisa call and all, because the spectrum is, they have shifted you to the Wi-Fi network. See, in 2G, the Wi-Fi network only used for SMS and all. We have not got an option for viewing movies and videos and all. And now in 3G, a little bit more Wi-Fi is being used. In 5G, only 30% of 3G data, rest of data is on your Wi-Fi network. 70% of your data has been shifted to Wi-Fi network, which means that the users can be dribbled in the physical domain. right? The number of users, earlier it used to be 1000, now the same network can go up to 3000, right? So you can increase your users and all and get back your money. Okay, and even if I reduce by half of the amount, still I get profit because 3 times I am getting users money. Okay, so this is one of the important phenomena which we are trying to exploit in the most of the communication networks. But can we use it for autonomous vehicle? Because
Sir, is it that migrating to Wi-Fi is user choice based or automatically it will be done?
automatic. You don't know that you have been shifted. When you receive a call and activate, your call is on Wi-Fi or LTE.
That is at the
You have seen that on the message you get on your mobile, voice over Wi-Fi, voice over LTE, voice over IP network and all. I think if you keep your mobile on, you'll get a message. Your voice is over LTE, your voice is over Wi-Fi and all. Right? Automatically it will be shifted. Okay? If at all a Wi-Fi signal is sensed in that area. If it is not sensed, then nothing can be done. Right? When you are trying to speak, if there is a Wi-Fi available, automatically your call will be shifted onto that. Okay, that's how we call it as sensing and communication. And nowadays, if you try to see, we don't talk simply on communication. We speak on sensing and communication. Both goes together. So as and when I sense there is a Wi-Fi, I shift it because in your mobile you get Wi-Fi and LTE. So automatically the mobile user knows that there is a Wi-Fi active on your network. So they shift you to Wi-Fi.
On a voice call, we find this particularly in the data transfer.
Data transfer.
There, when we are activating both Wi-Fi and mobile data,
then it will be shifted to Wi-Fi. Yeah. So this is one of the important things which you have to keep in mind. But see, you can see that only 30% of the users are using 5G, and rest of all we are only using Wi-Fi only for our communication. And this is very popular if you try to see your WhatsApp message or some message, what you are trying to say. All the calls are WhatsApp or Wi-Fi, right? So if your WhatsApp call can go, why can't your mobile call can go in that, right? So without your knowledge only we try to shift it so that the spectrum can be available on it. And if now in smart modes you have to activate that, voice over Wi-Fi you have to activate. Earlier it was like dumb phone, but now you can have a control on that. And there is another good reason why they are shifting to Wi-Fi. In some cases the 5G signal might not reach you, right? But you have a strong signal in your home with Wi-Fi. So if I shift to Wi-Fi, your signal quality can improve. That's how the service providers tries to tell you, saying that if you activate, you get better voice quality. Because why this problem of 5G and WhatsApp, Wi-Fi and came up is, when we try to model the channels, most of the channels are modeled based on the long existing models like Asian, Relic and Nakagami, and some channels we have used it. And the users density are increasing. For example, if there is an apartment, there might be 100 people staying in it. Earlier there might be only 2 or 3 in an independent house. So the user densities are increasing in a given cell, right? And when the user densities increases, the household articles tries to increase. And when the household articles tries to increase, the signal penetration tries to decrease. So the signal might not come to your place where you stand. So in that case, what they say is, we check both the signals. This signal is better because the Wi-Fi is closer to you. So they shift it to a better quality signal, right? So that is one reason what most of the theoretical things are there. So that is one of the important reasons also. When the signal quality is not good, the voice dropping will be more. The call dropping will be more. So the call dropping is again, if you see from the network point of view, we are not supposed to drop a call when a call is in progress. Otherwise, the service provider can be have to pay penalty. If you go to TRAI website and see the Telecom Regulatory Authority of India, they say that call drop is a fine, like the service provider has to pay a fine. So if you don't want a call drop, we have to give you a better signal channel. So this is one of the better signal channels. So there is a lot of regulatory activities which are there around it, which we are not supposed to speak it on video and transmit it, right? So so we have a 1200 megahertz signal bandwidth in your 6G Wi-Fi 6E, and this is almost equivalent to your 5G what is there existing right now with the base station. So if you try to see, you have outdoor and indoor around 600 and 600 for your downlink, and you can see that there is a standard power, we call it as automated frequency control, AFC, right? Automated frequency control. So there is a standard power which automatically controls the power which you cannot cross it. So with that, you can have a better transmission of 500 megahertz, you can use it directly. With a lower power indoor only, you can have a smaller powers, right? This is one important thing we have to keep. If you are going outdoor, you can increase the power, and in indoor you can decrease the power. And why actually we are trying to do that power management over here? Because it is a microwave, right? Electromagnetic signal, we are trying to use it. So when you continuously try to get exposed to the high power, it is like boiling yourself, right? In microwave, if you try to see, we use the same microwave frequency, but at a higher power, so that it gets cooked, right? And we are trying to reduce the power, and the frequency is same, so it takes a longer time for you to cook. So it takes around 20 years or 30 years for you to get that feeling of that. So that's how the power regulator has came up and said that you cannot use more than that. So that's how we try to limit it to almost like 1 watt, less than 2 watt only. You cannot go beyond 2 watt. Always it is around 1 watt, because if you try to see the standards for a lot of other countries, all are around 0.8, 0.7, 0.1, 0.2, 1 and so on, right? So that is the standard powers what we are trying to look at. And you can see at 2.4 you have only this much bandwidth, and 5.2 you have this much for the outdoor and uplink and downlink. Whereas here you can see that you have a wider bandwidth for that, and this is almost equivalent to your 5G, right? And this is from your Qualcomm paper. If you try to see, you get this picture. And 6G, even though it is not available in India, I think now the latest shipment what we get in Wi-Fi has 6E built into it. So now with that, you can think of completely connecting a building or a set of buildings around you, because the bandwidth is so high, 1 gigahertz. So now the future picocells of the 5G will be all Wi-Fi only, which will be giving you around 1 gigahertz bandwidth, right? And it can connect the complete area without any disturbance. On top of the building, if one pico base station has been kept, you don't need these wires and all running into your houses.
Is this already implemented? 6 gigahertz already implemented?
Yeah. If you try to see, they have tested in Ohio Stadium 2 years back for seeing whether all the users are getting the live video or not on their mobile, right? And everybody was very happy seeing the live, because they cannot see the match very closely, so they can see the what they call close-up shots and all, right? They can see live, but very far away, they don't know how they hit and all, so they can see the live on their mobile directly, all the people in the stadium. So even in some of the college auditoriums also, they have activated and tested it. And the products have been already available in US. In the US, they have released it, but we are also going to get it shortly with 6E. Next set of Wi-Fi's will be only 6Es. There will be no 5G and 2G.4 and all. Yeah. And now even the institutes like NIT, IITs and all, they should not think about the fiber and all these things. Just put a building top 1 and finish it off, right? So now the advantage what you get is lower latency, because the speeds are increased, the latencies will try to decrease, and you have a super wide channels. Earlier you have a very bad narrow band like 1 MB, 2 MB. Now you have 600 Mbps lines and all. right? So the capacities have been improved, the performance has been improved. And if you try to see the applications, like augmented reality and virtual reality, gaming, cloud computing, all these things are feasible right now. Because earlier, right now, if you play on 5G and all, the gaming is not that, the latencies are not that good that you get a live feeling, right? With this, I think people are very happy with the augmented reality, virtual reality. The telepresence is another important parameter where the remote patient can be monitored as if there is a patient standing before a doctor in the city, right? And to transmit one frame, the frame size will be around 1 TGB, right? 1 TGB has to be transmitted to doctor to have a real feeling that they are in front of a patient, to know what are the problems he has and all. I think you might have seen in movies and all, there is a screen on which, like a transparent screen where the person is visible and all these things. So, hologram. So they need 1 TB for each frame to be transmitted. So they need a bandwidth of that much. So for that, people are trying to see that the 6G will provide that. The 5G is unable to provide that, but 6G, you can see that augmented realities are coming up very fast. And telepresence is the next hitting a application on the 6G networks. Right? So these are unified communication is live videos, right? We have a conference, so you get a feel that they are sitting next to you, right? No, these are high only. Is high only. It needs constant supply. It will not run on batteries.
So drones to apply.
Drones we cannot apply that, but we can use it as a base station for the drones, right? And still we cannot use it because it is limited in distance. Only 100 meters and all, 200 meters and so on. 100 meters only, it's not even 200 meters also. So that's why they tested it in a stadium and all. It is not that they have given a city and they have tested it. It is only a closed small 100 meters, is just around 200 meters. It's like a stadium or like a campus, they can take it up. So the key technicality of the Qualcomm, what they referred it is, they use OFDM signal sharing. The modulation what they have used is OFDM for both uplink and downlink. And MIMOs also they have used for the increasing the capacities, right? And 160 megahertz channel capacity is given for a user so that he can upload and download his data and all at 160 megahertz speeds. And target wake up time is another significant one, which consumes less energy from the devices, right? So if there is required only, it will wake it up, otherwise it will make it to sleep, right? So when, the good example is a mobile phone. When I get a call only, it wakes up, otherwise it will rest. That's what we mean by target wake up time. And it uses 1024 QAM. We have done only 16 yesterday, but just imagine that it is using 1024 QAM modulation scheme. Okay, so you can think of the data increase how much time. Okay, and if you are trying to use the beamforming technique for that, so again the number of antennas will tell you how much you are trying to increase. Okay, the beamforming, if you have 12 by 12, so each one can go, and with that capacities you can increase. So I have shown you the capacity equation m into something, right? So the m you can increase it also. So and Wi-Fi protected access 3 is already in place, and people are trying to use it for even for the old Wi-Fi's. The automatic it can be, and there is nothing like a human coming into it and trying to transfer and all. It is interportability. The old one can talk to new, and new one can talk to old also, right? So if you have two Wi-Fi's, 5 and 6, both can talk to each other. Okay, you have downward compatibility, and these devices can also talk to the new devices. So this is something about the cellular, and this is the large networks. We'll take it up next class. And before that, if you have any questions, you can ask me. So we have only covered the lower one, short range only. And please remember that the short range is only for internal communication only. We are not trying to use it for outside downlink or uplink or with the neighborhood and all. So neighborhood we cannot talk is the distance is only few hundred meters. If they are quite far away, 1 kilometer, they will not be able to establish. Right? Okay, if no questions, we'll stop over here and we'll take 10 minutes break and join back. Yeah. Thank you all. So that we can do the experiments.
Sir, and one more thing. If we ignore the power constraint, we can use it as a replacement for, I mean, we can use it as a permanent solution for ad hoc network. Can we use it for?
We cannot be able to
As a
use
base
it
station.
because the power consumption of Wi-Fi is very high.
Okay.
If you want to use it, the battery will get drained within few minutes. Right? The maximum the battery can drive is 10 minutes or 20 minutes or 30 minutes. There are different batteries. But the problem is, as you increase the time, the weight of the battery increases. Right? And it might not be able to sit on the drone. Right? For example, I could ask you to put that car battery into that drone, you might not be able to carry it. Right? We want the size of the battery should be as small as possible so that the drone can lift it. If the drone have heavy weight, it consumes a lot of energy for lifting it up. Right? So it is not a feasible solution for drones. Okay? But what we can do is we can have a small Wi-Fi agent over there which can communicate among the device and give you information. Not a heavy Wi-Fi, low energy small Wi-Fi you can have, which can communicate among themselves and transfer. And instead of that, Bluetooth is sufficient for doing that, same distance. Right? And it can connect up to 7 to 8 devices. It is sufficient for monitoring. Rest of things you can have wired communication also. Right? If the Arduino is there, you have a Ethernet cable port also, USB also. So you can communicate among all the devices. Right? You don't need a wireless service over there.
Yes.
Okay? Because wireless services are uncertain compared to wired communication. Okay? So there are other options also available, but for a long distance it is not so good. For internal communication you can still have it, and to have it you can have Bluetooth, which is less power consuming than Wi-Fi. Right? We come in. Polynomials and rational functions also built into it, and you have signal processing as toolbox which can convert and transform data. Graphics interface is there for plotting, user interface and across environment. Optimization includes differential equation solver, linear matrix, inequality solutions, and dynamic compilations can link other languages such as Fortran and C, and this was developed long back, and recently there is a Python edition is also available in Scilab. Okay, and you have the numerical algorithms like scientific computing problems. Functions also, there are some functions built in, and libraries also, there are some functional libraries. So when you try to compare with the MATLAB, all the features might not be there, but for a small functionalities, this can be used, and the code also is similar, like MATLAB, what you write, the same code can be run on Scilab also. So you need not have to spend much time in learning about Scilab, you can directly use it. You can directly use it, but please remember that not all the toolboxes which are existing in MATLAB is available. And hence it is not that popular as MATLAB, because the functionalities in MATLAB is added advantage. They have a lot of functions which can be given it. So with this small introduction about Scilab, we are going to give you a set of experiments in Scilab, but we only run one command and show you how to use it for the execution of satellite link. Okay, so we start with that directly, assuming that the other routines you have run it, but we provide you the list of experiments. You can just run those programs afterwards. And basically we'll try to take one experiment and we'll try to explain what we are trying to do it. Okay, I am handovering the mic to Meghana. So here what we are trying to do is we are trying to, the top code if you try to see, the top code if you try to see, this is to generate the front end. Like we want to create a front end, you can enter the data and you can get the output and so on. So we call it a user interface. So this code is to generate only the user interface. It has nothing to do with your coding, right? So can you run it once? So if you run that one, you can see that we get a good screen over here. For generating this only we are trying to write that, okay, so that the user can enter his data and he can get the data output, right? So this front end is not MATLAB. We are generating that using some set of commands, this front end, so that the data from here can be passed down to the code. We call it a user interface, right? So here you can change colors, you can increase the style, decrease the style, boxes you can change it, everything you can change it, and you go back to the screen. And so here you have, so you can see that we have defined the handlers, left to right, what should be the diameter, and all these commands are only for generating the user interface, okay? So this can be modified. You can change these parameters to your requirement, whatever is you feel. You can put your name or you can put your college name and you can have whatever you want. You can just type it on that, right? Okay, next going to the code, if you try to see, from the handlers we are taking the data, right? And we are trying to compute you can see that you have 20 log TP into AGT, which will tell you the path loss, okay, the path loss exponent you can calculate, and then you can feed it and you can get back the signal. If you give the signal to the channel which has the path loss, and then at the other end we are trying to find it out, okay. So with this small introduction, the program will be executed, and you can see that if we give a transmit power of some dB, how much? Just 20 dB, and the gain is 2, right? Generally gain will be 1, but if you have a longer aperture of your antenna, you can increase it also, right? So if it is 2, and the receive antenna gain is also 2 pattern. So if you assume that similar type of antenna is there on the receiver, you can take 2 and 2, or you can take 1 and 1, okay. So enter the frequency of operation. What is the link frequency if you try to give, if I give 1.5 gigahertz or 1200 megahertz or something like that, you can see the losses, how much it be generated and so on. And system bandwidth you have to give it. So system bandwidth also should be equal to the frequency bandwidth, otherwise there will be too much of losses. You can just change that to 100 and you can, and if you change it to 1200 to some 1100 or 1000, so you can see the capacity decrease and all, and the channel is a constant channel. We have to change the channels also for different environments. If you take a standard 20 dB or 20 log something, you will get a standard channel. If the channel is a fluctuating channel, then you get a different values. Okay, we have taken only AWN, it will be constant for all the frequencies. Okay, so you can just have a understanding. The code is given to you. Just try to spend some time on changing the channels also. And if you can incorporate that channel, remove the channel and put other channels, what you have. And now you can run other codes also. We have given you a set of codes, right? You can just run those things up. Or you can keep for some time until they complete.
How to invoke that Scilab application?
User to Scilab, how to activate the Scilab. No, you just run it once. It is like you have to click on the file. What of file you click, automatically it opens in Scilab.
What is that file name? I extracted the folder zip file.
Okay, you close this one and open it again. Close this one. Close. Now you open that file. So it automatically opens, right? This is the Scilab environment only.
So from the beginning.
Yeah. You go to the field. You pick up a
Class LCW silence.
So you go to the Scilab directory where it has been installed, right? And in that directory, go to the bin directory, subdirectory, and in the bin directory, you can open it the Scilabs, and automatically you go into the environment window where you can open the file, whatever file you wanted. Yeah. You can pick up the file where you have written the experiments, the mobile experiments, and you can just try to pick up the file and run it. Right? There are set of programs which are there, which you can run all the programs, and this is one satellite link program. So I repeat it again. So the Scilab where it is installed, you go to that folder, and once you enter that folder, there is a subfolder called bin. Okay, go to the subfolder .bin, and in that you have Scilab, so you can just open that one. Automatically the Scilab environment will be open. So you connect to the directory where your folder, your programs are there, and then run the code over there. Pick up the codes. You have different types of channel allocation, estimation of BR for differential modulation. You have estimation of receive bit error energy, and there is some example. Okay. The multi-path pathless models are there. So there is exam lab 1 and 2 also you have to do. Okay. So these models you can run it and see it. Okay. And there is a help directory also available to you. If you go to the Scilab site, there are some codes available for you, which you can use it for other subjects also. Not only for this, you have for other subjects also. We have a lot of add-ons are there, because we have written 2 books for it. One is digital logic design and other is vision theory. So the codes are available over there where you can run it and see. Right? So the 2 books, what we have written is also available on the Scilab textbook, the version. So most of the textbooks have been converted into Scilab companions, and you can easily use them for your applications also. Okay, thank you. You can continue working. So once you complete, you can start installing the NS2. We don't have NS2 installation. You can రేపు experiments ఇవాళ NS2
Fine when you open